So it's recording. We'll start in less than a minute for those who are here. So only the person sharing the screen and who's actively speaking will have their image recorded.
So we've posted the link on the chat. For some reason, it says visualization in astrophysics, but it's really visualization of bias mitigation.
Sorry, let me correct that.
Yeah. And Sunipa, can you just repost the link after it's corrected because it won't update itself?
So it is 9:30 a.m. So in the mountain time, and I think we should get started. So Vivek,
Yep.
So Shri Kumar will start things off.
All right, folks, welcome. Just a quick logistical thing. This talk is being recorded and it'll be available online afterwards. Welcome to the AAAI tutorial on where we give you a visual tour of different bias mitigation techniques that have been applied for word representations. Before we get started, I just wanted to make sure that I alert you to this trigger warning. As this nature of the topic goes, this tutorial will involve examples of stereotypes that are out there in society, and this could be potentially triggering. For this particular tutorial, we've created a new tool that allows you to visualize how biases manifest themselves in word embeddings, and also how different visualization techniques, how different mitigation techniques reduce bias, how they operate. We'll be using this tool as for about 45 minutes to an hour in the middle of the tutorial. And the link is available here. It will also be pasted on the chat. We invite you to work with it as we go along. Just to kind of make sure that you're all credited, this tutorial is brought to you by a team from the University of Utah and the University of California, LA. You can see all our photos on the screen. So let's get started. Even though this is not really a tutorial about word embeddings, it would be remiss if we don't start off with what word embeddings are. Word embeddings are pretty ubiquitous. There's a good chance that most of you have seen them before, but I do want to spend a little bit of time talking about what word embeddings are. To kickstart the whole process, we need to think about what words mean. How do words, what is the process that endows words with their meaning? And by that, I mean, you see this string here, CAT. How do you and I both agree that it represents that thing that's in the image? And why is a cat closer to a dog in meaning than, say, a tiger or a table? This is almost a philosophical question, but maybe from the point of view of NLP or language technology, maybe the more pertinent question is, how do we represent the meaning of words in a fashion that that allows us to build interesting programs that operate on the semantics of words? And of course, this is an age-old question. There are many answers to that. Maybe one answer could be that we are trying to we can just look at the dictionary, but words have meanings even before they make it to the dictionary. One of the most productive hypotheses that has been proposed for quite a while now is the distributional hypothesis, that simply says that if two words occur in similar contexts, they should probably share some aspects of meaning. So cat and dog occur in similar contexts enough number of times that there's some amount of shared meaning between them. The pithy quote from Firth, 1957, is "You shall know a word by the company it keeps." So we need to characterize the distribution of the context of a word to understand what the word means. And there's some question about what context defines the meaning of a word. Usually in NLP today, it is interpreted as neighboring words in text, or even more in a constrained way, neighboring words in the same sentence even. But the context could be syntactic, it could be semantic, it could even be something in pragmatic sense. Another perspective on thinking about word embeddings. Oh, by the way, before we get into the thick of things, I hope all of you have access to Rocket Chat. It should be on the tutorial page. So feel free to post messages on chat if you have questions, or because we are all on the same Zoom page, you can also use the Zoom chat to post questions, or if you feel comfortable, you can unmute yourself and ask questions. Just be aware that the tutorial is recorded in case you feel shy about that. So another perspective on thinking about word meaning is to think about symbolic and distributed representations. Words are just strings. So TIGER is just a sequence of 5 characters. Why should it mean the animal? Treating them as just symbols doesn't tell us a thing about what they mean. But we do know, because of the fact that we understand these words, that cat and tiger are closer to each other because they're both feline than, say, a dog along one dimension. But cat, tiger, and dog are closer to each other than a table because they're all animals. And even though everything has 4 legs, a table is different. So what we need is a representation that captures similarities between similar objects. And this is the fundamental job that we want word embeddings to do for us. If you prefer a more operational perspective, we can just think about feature representations that go into machine learning systems. And we can define a feature representation where every word is allocated 1 dimension. So in this picture here, blue means the value is 1, white means the value is 0. And this really, the first dimension in this picture is the cat dimension. The 4th dimension is the table dimension. These are 1 hot vectors, and they have been used quite a lot in designing features across NLP. But the problem with 1 hot vectors, of course, is that if you take the dot product of any pair of these vectors, it's 0. Or if you prefer distances, all pairs of these vectors are equally distant from each other. So there's no notion of similarity that's captured. Alternatively, we can think of distributed representations. This is a different word than distributional, which was the hypothesis of Harris and Firth and others. Distributed representations, one perspective on distributed representations is to think of them as vector valued representations, where we have these latent dimensions, and every dimension defines some aspect of meaning, and the words, the word meaning is defined by membership to these dimensions. So the first dimension is maybe it's something about feline. So a cat and tiger have a high value there. The last dimension is about furniture, and only table has a high value there. And here, under this representation, the good news is that cat and dog are closer to each other than, say, they are to the table. There are many ways of generating these distributed representations, or word embeddings, or word vectors. Effectively, from the point of view of this tutorial, we're going to treat word embeddings as just a mapping from words to some vector space, which means we have to decide on a dimensionality and all that. This mapping could be a fixed mapping. In other words, it could be just a table where, like a dictionary really, where each word is has an entry that is really a vector. And there are many different such fixed word embeddings. This whole process, the field got a big boost in popularity after Word2Vec and GloVe were published. And then there are other fixed mappings like fast text, for example. In this tutorial, we'll be using Word2Vec simply because they are easy to load, and in particular, we'll be using Word2Vec because they allow us to, they are easy to package and download for you when you're going to use the thing. You can also think of word embeddings more recently. There's a word embeddings are treated as contextualized embeddings. In other words, instead of thinking of word embeddings as a table where every word is mapped to a vector, word embeddings are generated by a function. The function looks at the word in its sentence and this constructs the vector on the fly. One of the early successes in this was using this model called Elmo, but more recently, a lot of NLP methods are built with models that have the word Bert in them, like Bert and Roberta and Albert and such things. There are many contextualized word embeddings out there. Either way, today, almost de facto, they are the standard first step in any neural network model for NLP. So usually any model for NLP today looks like this. You have some input text, first you embed the words, and then you build a neural network on top. I'm not saying, I'm not going to comment on what I think about the fact that these are the dominant models today, but this is what it is. So this is really great. Word embeddings capture meaning. How are they constructed? Oh, but before we get on that, just to quickly summarize what we've just seen, there are a few different perspectives to think about word embeddings. They capture this distributional semantics idea. They operationalize essentially Firth and his cohort. They are constructed by appealing to the distributional hypothesis. They are distributed representations of words because they are words are characterized. The meaning of words are characterized by membership to some latent dimensions, and they also provide features for neural networks or whatever you want to do with them. So let's very briefly talk about how they are trained. We won't be touching this topic quite much more, but just very briefly, there are many different approaches for training word embeddings, but there are a few common themes. The first one is word embeddings are trained without using any labeled data. So you just use massive unlabeled text corpora, and you set up a surrogate learning task, which produces word embeddings as a side effect. So let me show a cartoon example here. Imagine that you have this sentence, it was a dark and dash night. You define a neural network where we try to find what word can go into the dash. So we define the probability that the word X goes into the dash. I have not written the conditioning here. Conditioned on the context is some function of an embedding of X and embedding of the context. And you train this probability to maximize this probability on available text corpora. And in the process of finding this probability distribution, what we have created as a side effect is all these embeddings for every word X and actually the context also. And if the word stormy appears here in the context, we try to maximize the probability of X, the dash equals storm. And we get word embeddings as a side effect. This process is computationally intensive, and this is going to be something that we'll bring up later. This can take hours or days or weeks to train, and that's an important point. Another thing to think about is how are word embeddings evaluated. At this point, we are not talking about biases. We are just talking about evaluating what information do word embeddings carry. And there are two broad approaches. There's intrinsic and extrinsic evaluation. Intrinsic evaluation requires probing these representations without appealing to another model. Extrinsic evaluations involve evaluating these representations on a downstream task. Intrinsic evaluations tend to be really simple tasks where their success or failure is really entirely defined by the quality of the representation. It doesn't say much about how their embeddings are going to get used. Extrinsic evaluations typically involve a neural network slapped on top of the embeddings and a particular task. They can be more practically useful, but they could also be slow because there are other factors that influence the evaluation. The famous intrinsic evaluation, of course, involves using word analogies, where the task is to complete this puzzle. Queen is to king is the same as tigress is to what. And one possible approach, there are many ways of solving, using embeddings to solve this question. One way of doing this is essentially to frame this as the search over words D that maximizes the dot product of the embedding for D and the embedding for A minus B plus C. If you are unwilling to parse, or if you don't want to parse the maths this early in the morning, another way of thinking about it is we want to find a word D such that A minus B is almost equal to C minus D. And among all the words in the dictionary, which word fits this thing? Now, and we will use, we'll revisit this analogies thing quite a bit. So coming to the point that of this tutorial, word embeddings are really great. They have made NLP they made NLP successful in some sense because they allow us to build NLP systems that seem to do really well in terms of their end use. We can, people who are not even trained in natural language processing can just treat this in the same way that people who are not, can use this in the same way that people who are not trained in the internals of a compiler can just use a programming language. So they have essentially broadened the scope and the use of NLP. That's fantastic. But if word embeddings capture distributional information from from the corpora that they are trained on, and the corpora themselves contain societal stereotypes, then the embeddings may encode these stereotypes. And that raises problems. Because imagine, for example, that these embeddings are used, say, in deciding whether a CV, should be interviewed or not. There's a fantastic quote that I found in a recent paper in the context of computer vision that I'm going to read out. It's on the slide. Feeding AI systems on the world's beauty, ugliness, and cruelty, but expecting it to reflect only the beauty is a fantasy. This is a paraphrase from Ruha Benjamin's book, which I strongly recommend. So this field of quote unquote bias and studying bias in language technology is a fast moving field. There are new techniques that are presented every month. There are new perspectives, new ways to think about it. And there are, broadly speaking, there are two related lines of work, at least from the perspective of this tutorial. There are new methods for quantifying biases that are encoded in embeddings, and there are methods for removing them. In this tutorial, we're going to show a visual exploration of various debiasing tools. First, we'll start off right after this. Jeff Phillips will introduce various notions of biases in embeddings. And then we'll talk about how we can measure the bias using intrinsic and extrinsic methods. And finally, we'll get to the last part of the theory part of this tutorial. Involves an overview of different bias removal methods in word embeddings. And then after that, we'll take a short break. And after the break, we'll go to an interactive part where we invite you to download a new tool that we've developed for visualizing word embedding biases. And we'll work through a bunch of examples that show how different debiasing methods essentially change the vector space. We'll wrap up with some critiques of debiasing methods and a discussion of where this field might be going. And this, we are hoping, will be like an interactive part as well, where you get to participate. All right, I will stop sharing now, and Jeff Phillips is going to take over.
Hi, so I'm Jeff Phillips, and I believe you should be able to see my screen at this point. So I'm going to talk about notions of bias. So as has been as has been set up by Vivek, there are a variety of so there's this huge use of these word vector embeddings, and these can carry notions of bias. And so I'm going to try and describe what those notions might be, and so how to think about them in this context where they arise, and so how to see that these actually exist in case you're not convinced yet. So if we think about this from the statistics perspective, right? So there's this kind of more mathematical, technical definition of bias, where it's the difference between an estimator and its expected value, right? So the estimator might be X hat and the expected value of EX. You could think of this as maybe there's some sample distribution, the black dots, the true expected value is somewhere in the middle, but maybe we have some estimator X hat here, right? And it's off. And the bias is this direction in between these two, or this difference in between the two. So there's another way of thinking about this. I mean, if you look this up in the dictionary or variety of dictionary, you see a variety of these definitions. And there's one from more, like sociology, which is more about, when there's, then bias is describing some instance of prejudice, and especially if it's personal so sometimes unreasonable outlook. And so in machine learning, kind of there's a related notion which I think captures what's going on slightly better, which is so-called like a stereotype. And so a stereotype is kind of a rephrasing of this slightly, possibly slightly differently. And it's an oversimplified view of prejudice attitude of a particular type of person or thing, right? Right, and so if we kind of boil this down to its kind of to its simplest aspects, what we can get is this is an oversimplification of a concept. So great. So as we'll see that these word vector embeddings capture these notions of similarity through their distributed representation, and this gives rise to these notions of concepts. And one way, and kind of a nice complementary way to think about a bias is it's an it's like an simplification of these concepts which are captured, right? And you can think of it both the statistical view where there's the true value, which is maybe complicated, and we have a kind of approximate representation, or we have some oversimplification of some concept in the space. Oversimplification of a context, this could be something fairly benign, like like children are curious. It could be it could be something like dogs are friendly, which is which in most cases is probably not a problem. But if you think a dog is friendly and then it's not, then that's a problem. But something which could be more problematic is the bias and stereotype captured by this notion that nurses are women and doctors are men. And this is kind of an oversimplification of what's going on. If you look at the kind of statistical percentages of this, or as it's captured in language, then this might be more true than not, but this is not so entirely true. This is an oversimplification. When we talk about bias and stereotype, there's often some sort of negative connotation with these types of simplification, right? Those are the ones that that children are curious. This is kind of harmless. We're going to talk about things that potentially can cause harms, right? And so this harms is this notion of thinking about how to speak about and quantify these notions of when actually some damage is being done. And so if you haven't heard about this before, I highly recommend this. This keynote by Kate Crawford at NeurIPS 2017. There's a great YouTube video about this. I'll go much more in depth about this. It's a great resource for this. And what Kate does is she introduces the idea of two types of harms. The first type is going to be called an allocational harm, and these are a little bit easier to see. These are things like if is someone accepted into college or not, right? If because of some bias or stereotype, you are not accepted into college when you're otherwise worthy, then this is a harm caused by that, right? Similar things happen in bank loan applications or recidivism prediction, which kind of will determine whether someone gets out on parole or not. And so all of these have there have been documented cases where there have been these harms that are in some cases related to these stereotypes. And maybe you haven't faced those yet, but maybe you've had the concern over did your paper get into AAAI? And so a lot of conferences are going to this double-blind format. One of the reasons for that is to try and reduce unwanted biases in the process, to reduce the potential harms of did your paper get into AAAI or not, right? So these allocational harms I think are pretty so clear to see so sort of conceptually what they are. But there's another type of harm, so which is more subtle. So that's called like a representational harm. And this is how the way that data is represented directly leads to negative stereotypes and biases, right? And so LaTanya Sweeney was one of the first people to kind of really make clear that this was happening. This is a picture from her website where she so if you search for this if you search for this researcher, so Ebony Bookman in Google, the sort of ads provided by Google, at least in at least in 2013, include things like so do you want to check up what her arrests were, right? And so she works at at the Genome Research Center, right? And she has a PhD, but because her name is so associated with being Black, these are the things that are sort of triggered. And this is, not an allocational harm, but there are some kind of more subtle harms which are occurring because of this. And so I think these representational harms are also really interesting to study because knowledge representation is a very large part of AI, right? How do we best represent knowledge? And these word vector embeddings are kind of a very powerful and very useful, highly used way of representing knowledge. So kind of we're going to be studying often these representational harms, although some allocational harms inside the context of these word vector embeddings. So if there is this bias which is arising, might question, so where is this bias coming from, right? And so this has been debated. There kind of one claim is that it's rising entirely by the choice of data, right? We're building these as a representation of some large set of data, but just because it's large, it's maybe all of Wikipedia or all of the internet, it does not mean that it's a fair representation of what's going on, right? Those are not kind of representing everything in life. They're more biased toward or more representation within them from Western civilization, right? Things going on in North America and Europe, for instance, get more represented in this data. But there's other aspects too, right? What is the mechanism to actually represent that data? We took this data, all this text data, for instance, from Common Crawl across the internet, and then we use the context of that data, of every word, to build its representation. So that was a choice of how to build these representations. It works well, but that choice might induce some sort of bias in it as well. And then when we probe these things, we often don't work at them just looking at the representation, but we'll try and put a learning algorithm model or algorithm on top of this. And this can give rise to other sorts of bias, right? And we'll see some of these issues later on in this tutorial. And these can translate into representational or allocational harm in various ways. It's important to think that when we're using these word vector representations as part of this complex machine learning pipeline, right? And I've simplified a view here, but it's still, this simplified view has several steps. There's the actual real world that we want to understand, and we want to make predictions about or kind of gain understanding on. We start by perhaps scraping some data. There's some choice of how we gather and scrape the data. We translate it into some abstract representation. This might be a word vector embedding. It might be something in between. Might be and then we use some machine learning black box perhaps on top of this, and we get out some sort of prediction. And so this bias and where bias comes into the prediction, which can cause representational or allocational harm, can happen at a variety of points in here, including steps that I've kind of glossed over in this process. And so it can be hard to quantify that it actually exists, right? For a while there was speaking of it, and there was not a consensus that bias actually existed within this pipeline. I hope that's changing at this point, but there have been some clearly documented examples. There was this study by ProPublica so a few years ago where they sent out some resumes to so a bunch of jobs. The resumes were basically identical, but one was represented by a Black person, one by a white person, and the distribution of the callbacks in these cases were in generally much favored towards towards a white person, right? This is a very controlled study which demonstrated this. It didn't pinpoint where it occurred in the process, but it demonstrated it existed. There's another kind of famous example about redlining, where loan applications were given out to neighborhoods. They were not allowed to explicitly use race, but they drew a red line around various zip codes that were predominantly, say, African American, and it was much harder or impossible to get a loan if your zip code was in that district instead. This actually led to some change in some laws even. This was documented well in that case. So these documented examples exist, but where's the source of them is a little bit harder to see. There are even more nebulous examples. This could be non-blind paper acceptances. This is hard to do a controlled study over. There have been attempts like the NeurIPS experiments about 5 or 10 years ago, but they weren't totally controlled in the sense of was bias occurring in those processes. And so in policing, this has been tricky because there's kind of some evidence that that police have been biased in certain situations, but it's harder to see because the police are sent out into neighborhoods that where they're sent out to have a higher rate of arrest, and so the data you're getting back have higher arrests and incidents because there are more police there. And so there are these confounding factors which are harder to tease out, right? So this is sometimes harder to kind of see where it's occurring, but it's definitely occurring in various places. So we can quantify these allocational harms exist, but hard to quantify exactly what the true source is. And so in this tutorial, we'll talk about some ways in the context of natural language and natural language processing tasks. And we'll look at some actual things kind of we're going to be using effectively as a proxy for these allocational harms, where we're going to be doing actual machine learning downstream tasks where we can consider simple and controlled experiments where we can definitely quantify that bias is happening. And it'll be over millions of evaluations. So it's not a small kind of anecdotal thing, but we'll be evaluating over this large set of data to kind of be more convincing. And we'll also be inspecting these representations. These are these intrinsic tasks that Vivek was talking about, where we can look directly at these sort of representational harms. These are in the representation itself, and we'll specifically look at these word vector embeddings, and we'll look at them from the perspective of their geometry. So let's start thinking about, I'll start introducing the geometry of these word vector embeddings. And the way I'm kind of a computational geometer by training, and so I like to think of them as points in 300, or in the demo that we'll use 50-dimensional data, so it's a bit smaller, but in some high-dimensional space, and these are really vectors from the origin, and they're designed actually so the similarity is preserved for words that appear in some similar context, like car and truck. Then the cosine similarity should be similar between these two vectors. That's how these word embeddings were trained. But it kind of encoded all these words in the same representation, and it kind of gave rise to these other sort of observations that are happening. And so one of them was that you could see these analogies in the text, and there's a geometric way of thinking about this. You could think of, okay, if we know the embedding of the word woman and the embedding of the word man, there's a vector between them. And we can translate this vector through a parallel translate operation. And basically this vector, instead of starting at woman, can be started at queen. And then we can look, what is the word closest to the endpoint of this? If we translate this vector from queen, it implies a gender transition, say from female to male, and the closest vector is often the word king, right? So this allows us to solve these analogy tasks. And this kind of was not the original intention of these embeddings, but this kind of structure sort of arose out of this kind of putting all these words in the same space. But if you think about this, there's this vector which exists, independent of just two words, but is representing the gender somehow. So within this space, there is some sort of, concept vector or one-dimensional subspace, and so along it, you're moving in a gender direction, maybe from female to male. Okay, and this is kind of a cool thing which is arising out of these structures, possibly accidentally. But then what has been observed is that you get these other sort of words are in this space, such as the words, so nurse and doctor. And as it turns out, nurse tends to be much more on the female side of this direction and doctor much more on the male side. And this representation is encoding this stereotype, right? This simplification of a concept of gender gets encoded that nurses are more associated with females and doctors more associated with males, right? We can observe this directly in these representations, right? And we'll look at things like removing this direction and you get the data without this, and then doctor and nurse might be similar to each other, but there's no longer encoded this gender information. And we'll see other ways of thinking about this. This is just a warm up. Okay, so there are other more kind of algebraic ways of calculating, measuring these association and stereotypes. The most well-known is this wheat test, which is looking at this implicit gender association, but there are other ones as well. I'll mention this, this ECT test, and they kind of aggregate over a bunch of sort of similarity type tasks over some data, which might potentially kind of imply stereotypes in the sort of ways you would use this, but by looking at this representation in some sort of intrinsic way. It's local geometry. So what is this wheat test? So this was derived from these kind of long-standing studies within sociology about how words are potentially have a stereotypical association with them, and it builds on these word lists, and then it mechanizes them through measuring this with things like cosine similarity. And so it starts with two words lists, X and Y, where X is a bunch of definitionally male words, man, male, him, his, and then there's a female set. So woman, female, her are going to be in this set. And then it comes up with, and there's a few variations of this, but there's one with professions or occupations, where you may have these stereotypical male professions, programmer, engineer, scientist, and stereotypical female professions, nurse, teacher, and librarian. And so this idea of Caliscan et al. Was to measure this in these word vector embeddings using something like the cosine similarity, right? And so for a particular word, for instance, the word man, it compares it against these two lists, A and B, and looks at the average cosine similarity with these stereotypical male professions. And so if this is the word man, this might be high, and a bunch of stereotypical things, and the cosine similarity with these stereotypical female professions. And so if this is so you expect this not to be high, if there's going to be a stereotype, and it kind of aggregates these things together. And so you expect for a male word this to be high if it's associated with male professions and not female professions. And then you aggregate this over all words in the X and the Y set. You basically average over these. There's some normalization that's going on here, and you kind of measure this overall kind of association across these kind of all pairs across these sets. And so this overall score, the way it's normalized, it has to be in the range between -2 and 2, where 0 would be completely neutral, and 2 would be completely stereotypically associated with these occupations and male words. And for things like word to vec and glove, these are reaching things of above 1.8. So they're quite stereotypically, there's high kind of levels of stereotypes encoded in these. Right, so this is the most popular approach to do this. Kind of one of the first to kind of try and do this. There are other ones as well. There's this, so embedding coherence test is another example. And this looks at, instead of all words in the set, it computes a single representation, an average of all the male words and all of the female words. And then it does some comparing rank order against all of the sets A and B. And it is comparing these with a Spearman coefficient. One would be completely correlated, which would mean there is not a lot of bias between these, but you see things like glove is less than 1, and so there is some bias encoded in there. So these are ways to show that bias is encoded directly in these sort of embeddings. Okay, so this might be convincing, but as these have been published, there's been some say, well, is this really affecting how it's affecting downstream tasks within this machine learning sort of pipeline? And so there's ways to probe this through natural language processing tasks, right? One way of possibly doing this is with this problem of co-reference resolution, where you're getting these paragraphs and you're trying to understand with a pronoun if it is referring to the word doctor, or if it's referring to like she referring to doctor, or something else. And implicitly, if she was a doctor and it was kind of encoded in here that doctors are stereotypically male, this would be harder to do. These standard tasks are actually quite messy because there's a lot of things other than, say, gender or that would encode bias that is being used to make these decisions. One thing we're going to talk a bit more about is this task based on natural language inference. Okay, and so these tasks are set up with two simple sentences often, with a premise and a hypothesis. And what we'll talk about is having a simple thing like a doctor bought a bagel, and considering a hypothesis, a woman bought a bagel, and to see whether the first sentence implies this, this second sentence is also true. And this is kind of a fairly well-studied task. We will kind of, for instance, there's this this EMNLP paper from 2016, and what it gives is an output where it has either an entailment, which you think it is entailed, the second hypothesis is entailed by the premise, it's contradicted, or it's neutral. It doesn't say either way. And so we'll test this in a controlled way by having two different types of hypotheses, one with the word doctor replaced by woman and one with replaced by man. And you'll get things like, when you run this on, say, the glove embedding, you'll see that the woman hypothesis is a contradiction with 91%, whereas the man hypothesis is entailed with 84%, right? So this is encoding a type of, so it shows how in this downstream task, there is this gender bias encoded into this process. So, okay, so that was one simple experiment with three sentences, but you could think of kind of creating a huge number of these tasks, right? And so one way of approaching this is to create these large set of templates. For instance, there's this paper from AAAI last year, which considers a template of 164 occupations, 27 different verbs, and 184 objects, right? Like bagel, and looks at all pairs of these and swaps these out with man and woman, or with I think it was also gentleman and lady, and there are 3 pairs here, which were definitely male or female, and kind of you can look at the aggregate over all of these tasks. This is about 2 million different kind of premise with 2 hypotheses, and you can compare their entailment, contradiction, and neutral probability. Okay, and so for each of these, we don't know if the doctor is a woman or a man, so presumably it should be neutral, right? So we'd like the neutral rating to be as high as possible if we're able kind of, show there's not bias in an embedding, perhaps after some process we've implied on it, then we'd like the average neutral rating to be as high as possible, right? So one measure is just the average over all of the neutral values on these 1.9 million templates. But there are other ways you could aggregate this. One is the fraction neutral. That means the fraction of the 1.9 million templates where the neutral is larger than the entailment or the contradict. So if I were to try and make a prediction, pick one of these three, is it neutral, is it entailment, or is it contradicted? What fraction of time do I predict so neutral? In both cases, if there's no bias encoded, it should really be a value 1. So we want this to be as large as possible in between 0 and 1. So these give some notions of, and so this has been done, and we'll see some results later in the context of some methods to try and sort of remove the bias. But these have been demonstrated over these that there is definitely some bias that has been encoded in these representations through like the wheat test as intrinsic measures, looking just at the representation, and in these fairly controlled downstream tasks where we can measure it in this extrinsic way, in how it's used inside this machine learning pipeline. So this kind of a notion of bias in these word embeddings. So the next part of the talk will be about these methods for removing, for debiasing these word embeddings. And so Sanipa Dev will be giving this part of the talk, but if you have any questions while she is setting up her part of the presentation, now would be a good time to ask.
So there's a question, from Via. Image recognition resides that stripes colors is more likely a zebra. Is it biases?
Yeah, so I would classify this as like like a stereotype. I would think of this as an oversimplification of a concept. If you painted stripes on a horse, it might still be a horse, but you've oversimplified the concept here. Is this biasing that everything that is striped should be a zebra? So you could say it's a bias, but I would say that typically the things we'll focus on will be things that carry these sort of negative connotations, and this might lead to harms for horses or zebras, but I would say they're less kind of so tangible than the other sort of things we're talking about. So if you want to call that a bias, okay, but I would, in this tutorial, we'll focus on things where we can describe some sort of harms that are resulting because of these oversimplifications.
Okay, I'll start this next segment now. Please feel free to put in more questions in the chat and we'll get to them soon. Or stop us if you want to ask questions then. So far we have looked at this notion of bias and what it means for word embeddings and how they manifest themselves in these representations. So we see that they occur in the form of these implicit encodings, which propagate different stereotypes, whether it's about different occupations and the gendered notions that they might carry, which are biased or unfair. At the same time, there are other kinds of biases, like say those which propagate negative connotations about different nationalities or different races, and so on. So given that there is a large amount of bias being implicitly encoded by these representations, and which can also potentially cause harm downstream when we apply these representations to different tasks, it's important that we have different methods of intervention so that we can mitigate these biases before we actually deploy the embeddings in different tasks. So when we think about how do we intervene, the first question is, how does the bias come in? Because that helps us understand where we can exactly intervene to debias these representations. So The sources of bias, the most intuitive one amongst them is that of the data itself that we're training our representations on. So this is something like, say, Wikipedia or Common Crawl, or any large text corpus that we train our representations on. And because these large data sets see different distributions of word groups with each other, they lead to preferential associations in these representations. So historically, it might have seemed that a specific gender is more associated to a given occupation, and that gives us the statistical association later on. But if that's used for predictions of whether somebody can actually be in a specific occupation, then it can lead to unjust outcomes. So this is a primary way in which biases can get into these representations, but this is not the only way. There is also algorithmic bias, wherein these biases get reinforced by the mechanisms that we use to train our representations. So it has been seen that even if there is very little bias in the data set, it not only gets picked up, but also amplified by the mechanisms that we use to train them. So this is another point where we can intervene to reduce the kinds of bias that we see later on. Alongside, there are also other ways biases get into the entire system or the entire pipeline, and this is much later on, wherein we have already determined the task towards which we are going to put our representations. And then the data set that we have for that specific task can also have these different imbalances, which have like different representations or different sort of distributions for different social groups, leading to a larger amount of bias being seen in the task. So these are all different ways in which biases come in, and this actually gives us an idea of where all we can intervene so as to have lesser bias or lesser stereotypes being propagated in different tasks. So the first way to think about how can we debias embeddings is, of course, going to go back to the data set itself, wherein we try to balance out the different distributions that are seen in the data set. So this can be done by augmenting the data or balancing out different word associations. Alongside, we can also modify the embedding generating mechanism so as to encode lesser bias. So here we explicitly make the algorithm not only optimize the amount of information that it's learning from underlying data, but also minimize the amount of bias it learns. So both of these are effective, but as we'll see soon enough in a few slides, that these are also expensive. And as a result, an alternate method of post-processing of embeddings, which is less expensive, is a preferred route of actually debiasing these representations. Now, all three of these ways are very general in that we do not really need to know the end task to very fine, minutely, we do not need to know all details about the last task that we're going to apply these representations towards to debias them in these ways. But in addition to any of these methods, we can also debias whatever results we see of a biased nature in a task by balancing out the data set that we train this specific task on. So this is in addition to any of these three methods, and I won't go into details about this because it's very specific to every sort of application at hand, but I'll talk a little bit more about the three general methods and why one of them is more preferred amongst the others. So the first amongst these is that of data augmentation or data balancing. So here we begin with this corpus. Let's say we have a Wikipedia corpus, and it'll have different distributions of these word groups already existing in the corpus. So now what we do is we begin with a very naive setting. Let's say we begin with this man-woman setting, and we want to balance out their distributions with different occupations, adjectives, or other stereotypes that might be there in the data set. So we have this list of word pairs like man, woman, boy, girl, he, she, mother, father, and so on. And every time we encounter a word of this word list in the corpus, we flip it with different probabilities to the other word in the word pair. So we do this with 50%, 75%, and 100% probability. And this gives us 4 distinct corpora on which we can build our representations. What we can do now is compare these 4 representations to see which of these actually ends up having the least amount of bias. Intuitively, we would expect that at 50% or 75% is where we end up having about the least amount of bias. And to some extent, that is about true, because if we talk about the analogies, like what Jeff mentioned earlier, so if we wanted to evaluate bias just based off of those analogies, the analogies which began with word pairs which were in the list were actually going towards something better or like something meaningful rather than something stereotypical, but it was not a holistic improvement. So if we actually measured the word embedding association test scores, this would not really give us any improvement. And we can see why that would happen. We are just changing a very specific set of words while leaving behind a lot of other words, like say names or other words, which could encode bias as is. So there is a lot of bias still remaining in the representation or in the data set as well, which is coming through in the representation as well. So to take a closer look, let's just look at these word pairs like man, woman, boy, girl, he, she, and so on. Let's take the difference vectors and have their principal component analysis. So we have the principal values here. And if there is no gender component that is prominent, then the plot would have looked somewhat like the second plot at the top, which is that of random Gaussian vectors. But it's not like that. We have a very prominent first component, which is encoding this difference in gender direction, which is where the bias lies. So when we debias it by different methods, we would expect that this plot would start looking more like the second plot at the top, which is that of the random vectors. And when we do a 50% flip, which is the first plot at the bottom, we see that we do not actually approach the random plot as much as it should. Like it's somewhere in between. So while it has maybe reduced some bias, there is still a primary component which is encoding the bias. So if we look at the 75% flip, now we see that almost a second component has been added. And this plot is further away from the random plot as opposed to the 50% flip. And at the 100% flip, we see that in fact, we have actually added a second component, which is encoding the bias instead of removing the first one. And we can see again why this would happen. While we have removed or balanced out some words, we have not done this for like all of the words possible. So instead of removing the first component, which is encoded by the other words in the space, we have added a second component, which is when we have flipped the words to the other word with 100% probability. So this is clearly not the appropriate way to go about reducing the bias in the data or in the representations thereafter, because we end up with a lot of residual bias when we just balance it in very naive ways such as this. They're also less generalizable. So even if this was perfect, if this was actually giving us the plot of the random Gaussian vectors where we do not have a principal component encoding the bias, we cannot really do this for biases which do not happen in pairs. So it's not even generalizable to gender bias in general. So that's a major impediment. And even if we have more nuanced ways to actually go about balancing or augmenting the data to remove all of these biases, it's still very expensive because it requires us to retrain the entire embedding from scratch to see the debiasing in the data reflecting in the representation. If we think about all of the representations currently being used, like say Roberta or BERT, they train over a few hundred gigabytes of data, over a few days with a lot of computational power. So every time we want to remove a specific kind of stereotypical association, if we have to retrain these embeddings, it'll be very expensive and thus very inaccessible. So this makes data balancing a little infeasible as opposed to something that would be able to be less computationally expensive. So let's try and see if we can achieve that with using a way to modify the embedding mechanism itself to encode lesser bias. So one approach which tried doing this was this variant of GLOVE called the gender neutral GLOVE, which put in its objective function itself this added restriction wherein gender could be learned only along specific directions, and the other dimensions of the representations could not learn any gender associations at all, and they had to be about equal to the male and female gendered words, which was being learned in the separate dimension, which was restricted to gender alone. So again, this was effective for removing gender bias, but again, it was something that required pairs to be considered. So it would always have to be done in a pairwise manner, and it would require retraining of the entire embedding. So this again is expensive because we would need to determine the objective early on and retrain based off of what biases could potentially cause harm in a given task. So this too falls back with the same thing with as data imbalance or trying to augment data to remove biases, wherein both of these are quite expensive and prohibitive. Is there a question? Sorry. Okay, I'll go ahead. That's primarily why post-processing is a preferred method of debiasing, because it's much less expensive. What this does is it irrespective of what data set or embedding mechanism has been used, it just uses the representations themselves and finds this reduction of bias that it then mitigates in different ways that I'll go over in a little bit to remove and like reduce the amount of biases encoded. So this makes it more generalizable because we can find different concept subspaces in a more general manner. And also it's very inexpensive because these are usually computed like with using geometric operations on the space of representations and can be computed on the fly. So we do not need to retrain embeddings or like have a very expensive layer put into our system. The first step, however, is to determine the concept subspace, which actually captures this bias. And this is important because, as Vivek mentioned earlier on, that ubiquitously language representations today are distributed embeddings. So we do not have this feature to dimension mapping that could tell us where exactly the bias is located. We need to actually put an effort to find out this subspace. So there are 4 methods of doing this that we have included in the interactive tool, as we'll see soon. And I'll go over each of them now. The first one is of PCA paired. So what this does is it takes pairs of words like boy, girl, man, woman, he, she, and so on, and it finds difference vectors between them. So each of these black vectors here is basically the difference between the vector woman and man, or girl and boy, and so on. Now, these different vectors is what we use, and we try to find, we do a PCA analysis again, and we find the first principal component, and this encodes the direction of gender difference here. And this is where the bias lies. So while this is very simple and effective in this particular case, it's less generalizable because words like word pairs like boy, girl, or he, she are not really there for different kinds of biases. To simplify this, one way is to just get rid of these black vectors or the difference vectors. Instead of taking pairs now, we just take these words themselves. And on this, we do our PCA now. And the first component along this actually is the direction of gender in this case. So it's more general and it captures the direction where a lot of biased associations might be there. Another way to simplify is to just take groups of words which are statistically more associated to the 2 social groups that we are trying to find or trying to determine if there is any bias between. So here we have statistically or stereotypically male and female names. And what we do is we find the means of these 2 groups of words. We find the direction of difference between them by just doing a difference and then normalizing it. And this too encodes the direction of bias in this case. Another method is that which uses classification between 2 groups of words. So again, we have these groups of words which are statistically more associated to the 2 social groups in question. We require a lot more words in this case because we are doing a classification between them. These are just examples here. And what this does is it finds the classification boundary between them, and the normal to it now captures the direction of bias. So these are 4 distinct ways in which we can determine the direction of bias, and we'll see more about them in the tool later on. But once we have determined these directions of bias, the next step is to modify the space in a way to mitigate or dampen the amount of bias encoded. So there are 4 methods again for debiasing these representations in a post-processing way that I'll go over and will be a part of the tool. And we'll see more about each method with examples later on. But to give an overview of what these do, let's first look at linear projection. What linear projection does is that it has this direction of bias already determined using any of the 4 methods that I mentioned just now. But after it has this direction, it considers every point to be about the same in the sense that irrespective of what word it is, whether it's a gendered word, it's a word like car or cat or a country, irrespective of what word it is, it finds its component along this direction of bias and removes it from the representation of the word. So we can see that all of the words in the space now have no component along this direction of bias. They're orthogonal to it because it'll go down to 0. So what happens is if these points were lying in some n-dimensional space, they're now lying in an n-1 or n-2 dimensional space where they have retained all of the information apart from their component along this direction of bias. So let's go over an example to see what this looks like. So these points in orange and green are gendered words which have been used to find the subspace, but all of the points, like the ones in purple, all of these points, as we saw in the earlier slide, all of them actually get debiased the same. So this is just to show what we use to find the direction. So as we can see, there is a clear direction of gender difference, which also encodes this biased association with different occupations, with nurse and receptionist being more female and mathematician and scientist being more male. So this is a clear sort of bias that's being propagated here. So what this method does is, given this direction of bias, it simply projects them in a way that their component along the direction of bias is taken to 0. So here we see that they no longer have any component along this direction of bias anymore. If we do a PCA projection to see how it looks like in the space, we see that now these male and female words have almost converged to a point, and they have lesser association that's like preferential to either of these occupation groups anymore. So this helps in reducing the amount of bias that the embeddings have. Now, the next method that we'll go over is that of hard debiasing. Hard debiasing also relies on projection to remove the amount of bias in the embedding space, but it does it in a different way in that it first segregates the words out into different groups. So words which are here in dark green are the ones which are left as is. So these are the words which have been used to determine this direction of bias. So we could have used any of the 4 methods that we went over earlier to determine this direction. And these are the ones which are not moved at all in space. They're left as is. So they're lying in the high dimensional space that they were already in. For most of the other words, which are the ones in purple here, they're actually projected to remove and their component along the direction of bias, identically to what we did with linear projection. But in addition, there are also words like he, she, himself, herself, which occur in pairs. And these are the ones in these like green and pink points. And these are equalized about this axis. So what it does is it projects all points first and then reintroduces gender in a very controlled way into these pairs of words so that they have equal component in opposite directions along this gender direction. So this is done to retain some amount of meaningful information about gender, like say, he is still close to man and she is still close to woman, but they no longer have like that component which associated them differently to different occupations. So if you go over an example again here, we see how initially there is a gender difference here too. It's a very similar example to the first one. And here too, we see how nurse and receptionist are more towards the female side as opposed to mathematician, which is on the male side. The first step is to do the projection where all points are moved so as to have 0 component along this direction of bias, apart from these words, which were in green earlier, but here we just have them in 2 colors because one is female set, one is a male set, just to show the difference. But these are the ones which have been used to determine this direction and thus are unchanged in space. Next, the points that were paired are equalized. They are pushed back along this gender direction in a very controlled way so that they have equal and opposite components along this gender direction. And now in the final space, we again see something similar to what we had with linear projection, where we still have meaningful information, a little bit more as opposed to like linear projection, because we ensured that definitionally gendered words were not changed or they were pushed in a way to retain some amount of meaningful gendered component, but their like associations to occupations now is not as pronouncedly stereotypical as before. The next method is that of iterative null space projection, or INLP. And here too, it's the core operation is projection, but again, we do a categorization of words first. So the points in blue here are the ones that are not debiased at all. They're left as is. So it's from a predetermined list of words, which tells the function to not touch them at all. They're left in the high dimensional space. But all other points are projected. But before that, there are 2 groups of words which are used to find the classification boundary, and the normal to it captures the direction of bias. So this method only uses the classification method to find the direction of bias. And once it has determined the direction of bias, it does not differentiate between these points, the green, orange, and purple. And they're all projected the same way to have no component along this direction of bias. But what this method argues is that even if we remove one direction of bias, there could be other directions still remaining, which could encode residual bias along the same, like say, gender component or whatever we have removed initially. They might still be remnants of the same bias, which could still be captured. So what it does then is it again finds a secondary direction of bias using the same set of words And then it projects again to a lower dimensional space where it removes the components of these words along this direction. So it does this iteratively until a threshold has been reached where sufficient amount of bias has been removed. In about 300 dimensional space, 35 iterations is what it approximately takes to remove a majority of the bias. So let's go over an example of this as well to see what this looks like. So here we see that these points, we can actually have a classifier between them, which differentiates them. And we have this direction that's normal to them being the direction of bias. This basically changed the frame of our frame of view. We just align the gender axis with the x-axis so that we can actually see that there is indeed a difference which between them that we can classify between these points very easily. So this is clearly the direction of bias. It's normal to this classification boundary, and we see how different occupations are on each side. So what this does is it projects all points to have no component along this direction of bias. And then again, it finds another direction of bias by classification. Let's align this as well with the x-axis to have a better view. So one thing we should note is that while it looks clustered here, it's actually in a very high dimensional space where we indeed might be having still remnants of bias that can be encoded by different directions. Also, we've used very few words here to give an example, but this is done with like a large number of such words to find the classification boundary. So we can actually go over several iterations to remove this bias. So again, with the projection step, we are able to remove this bias or the component along this direction as well. And we see that this ends up giving us a space where the preferential associations to different occupations is much less. And we can't clearly have this classifier between male and female words, which also classifies like stereotypically male and female occupations. Now, the last method that I'll go over is that of OSCR, or orthogonal subspace correction and rectification. What this does differently is that it does not rely on projection to remove biases. Instead, it first identifies a subspace like say gender using words like man, woman, boy, girl, he, she, and so on, using any of the different methods. And then it also identifies a second subspace, let's say occupations. What this acknowledges is the fact that biases don't lie alone in a single subspace. Like for example, gender, the associations it contains within the subspace are mostly meaningful and not like stereotypical. The same is true for occupations. So when we remove any of these subspaces by projection, we are not just losing out on like stereotypical associations, but also meaningful associations which could be there within each subspace. What we instead want to do is take out or remove the associations between these two subspaces. So in English, for example, most of the occupation words don't really have a gendered connotation in like the dictionary, for example. Like the meanings themselves do not have a gendered association, but because of the data that we have trained our representations on, they do end up having like gendered associations. And that is what we want to remove. So the associations between these two subspaces are what we want to remove without actually compromising on any information within each individual subspace. So what we want to do is just identify the subspace and orthogonalize it in this space, or make it like rectify it with respect to gender in this space. So what this method does is it first identifies these two subspaces using these word groups, and then it proceeds to orthogonalize it. So it finds the component of this direction that is orthogonal to the first component, and this helps define a new basis. So occupations prime and gender is the new basis within which we want to move all of our points so that their components along these two directions are also orthogonal to each other. So what this does is we can imagine that if we have a point X in space, depending on its position, so its angles with respect to the two subspaces, it's moved with a graded rotation so that its components along the two subspaces are orthogonal. So its component with occupations and gender now in this new space will be orthogonal to each other. So this is like a shearing of space that we're doing, or a graded rotation that is applied to the entire space, so that occupations or all words along occupations, they retain their like meaning, and the same is true for gender, but any associations that were there within or amongst them are now orthogonalized. So all words now have a component along these two subspaces that are orthogonal to each other. So let's take an example or look at an example of this as well. So here we have words like he, she, along this axis. And we see like occupation words here, which do have a preferential component. We also see how reception is really close to the second concept subspace, which is that of occupations. So what this does is it orthogonalizes this, and we see how receptionist actually moved with this concept subspace. So it now doesn't have a component along the gender subspace like it had before. So we've been able to orthogonalize these different concepts without having to remove either. If we just look at a normal PCA projection of these points, we again see a similar result where they do not really have as much of preferential associations as opposed to before. So let's do a quick overview or a recap of all of these different methods and the differences they have. So the first point is that of how many subspaces do we need to determine to actually use these different methods? Hard debiasing and linear projection require one subspace each. OSCAR requires two, which are the two distinct subspaces it's orthogonalizing. INLP considers the number of subspaces determined to be a hyperparameter. So it keeps doing it iteratively until sufficient bias has been removed. Now, each of these subspaces can require word lists for their determination. And all of the different methods require only one word list for this step, except for OSCAR, which requires two for the two distinct subspaces that it determines and then orthogonalizes. But these are not the only word lists that these different methods can require. They can also require additional word lists to help in the function of debiasing itself. So hard debiasing and INLP, for example, require these word lists, which help in the categorization of the space as to which words to debias and which words to not debias. So this is their attempt to actually retain meaningfully gendered or meaningful associations within the subspace that they're trying to remove bias from. In addition, hard debiasing also requires another set of words which equalizes these pairs. So these are word pairs like he, she, or mother, father, aunt, uncle, and so on, which are equalized so as to retain some meaningful component along the direction removed. And this is the step which makes it a little less extendable to different kinds of biases, because in different kinds of biases, we don't really have pairs of words. But apart from this, all of these other methods are fairly extendable. And OSCAR, in fact, doesn't even require an extra word list to help debias different words differently. While linear projection also doesn't require an extra word list, it also ends up losing more information because it does not try to specifically retain information in specific words. But OSCAR does this in a more fluid way, wherein depending on the position of the point, it's debiased differently or rotated differently so as to debias a little differently. And if the words were along gender or occupation subspace themselves, they do not lose out on meaningful associations within each subspace. So this can be more effective because determining beforehand an entire list of words which might have meaningful components along the direction that we are trying to mitigate bias from is something that is not very feasible, given that the vocabulary size in most languages is like over hundreds of thousands. Now, extending to contextual representations is also very important because they're used much more prolifically now, whether it's Roberta or Elmo. These representations differ in the way that for every word, we no longer have a single representation, but depending on the context that they have appeared in, we have a different representation for the token. So a naive way to mimic what we did for, say, context-free settings is to just take these representations and then take the average of all of the different representations, irrespective of what context they appeared in. So say all of these kings give us one representation and all of the queens give us one. And then if we take the means of this and we find the direction between them to do very similarly find the direction of bias as what we did for Guelph, what we find is that this vector is actually more noise than signal, as we would expect, because we have conflated so many different distinct representations meant for different word senses into a single representation. So it behaves like a random vector, and debiasing with respect to this does not really give us much benefit. So instead, what we can do is we take both of these or any of these different representations, and all of them actually have a first layer that is very Gov-like in that they are context-free. So what we can do is we can just debias this layer alone, and then let this debias layer be the input to the rest of the embedding mechanism. We find that this itself is sufficient in debiasing these representations very similarly to what we get with, say, Glover word to vec, and to a very similar extent. So just this, this is a very simple way of actually extending any of these different methods that we'll go over today to contextual representations as well. But how do we actually know that we're able to mitigate these biases when we use any of the different methods that we discussed? So this takes us back to the evaluation methods, because debiasing always begins and ends at this point, because we want to know if there is bias along a specific direction and how much, and how we've been able to reduce it by using any of the different methods. So as mentioned, as discussed by Jeff earlier, we have the word embedding association test, or the WEAT test, which looks at these different word groups and the difference in association between them. So if there is less bias, then the score is close to 0. So more the bias, higher the score is, and lesser the bias, the lower the score is, because that means that the preferential association between these different word groups is about the same. So let's actually test this out on Glove. Let's see for like wheat with respect to occupations. First, we fix the gendered words. These are the word sets in red in this picture. So these are definitely gendered words or correctly gendered words. And we want to see if they have any like preferential association to stereotypical occupations. In Glove, the score is very high. So indeed, there is a large amount of bias being encoded. When we use any of these different methods, for linear projection, hard debiasing, INLP, or OSCAR, we see that these scores actually reduce significantly, and OSCAR actually ends up with the lowest score because it's specifically trying to disentangle occupations from gender. Additionally, let's look at if this carries over to a different sort of space. So we've still like debiased with respect to occupations for OSCAR, and for the other three, we've just removed the bulk of gendered associations that are stereotypical. And we want to see if they still have stereotypical associations with home versus work-related words. So home-related words can be words like family or cousins and so on, and work-related words are like corporation, salary, and office. So these are the exact word sets we have used. And here too, we see that there is bias encoded by the representation of wealth. And it's lesser as opposed to that with occupations, but it's still like not 0. And when we use any of the different debiasing methods, we see that we are able to reduce this significantly, and they're actually quite comparable in this, but INLP ends up having the smallest score, so it has removed the most bias in this case. Let's see if the same is true for the extrinsic task, wherein we are using NLI as our probe, and we have these sentence pairs, and each of them should have been classified as neutral because the premise never tells us about the gender of, say, the occupation word there. So we don't know if the doctor is a man or a woman in this case. And thus we would expect that the classification would be neutral with a very high probability. But since this classification has an inverse relationship with the amount of bias, so higher the classification of neutral or higher the probability of classifying as neutral, we know the lesser bias there is. We're able to use this as a proxy to see how much bias there is. So ideally, both of these scores of fraction neutral and average neutral should have been 1 because of the way we've set up the sentence pairs. So fraction neutral is looking at the fraction of sentence pairs actually classified as neutral. So this should have been 100%. And average neutral is the average probability of classifying a pair as neutral over the 2 million or so sentence pairs evaluated. This too should have been 1. But with Glove, we see that both of these values are actually less than 1/3 as well. But when we use any of these different methods, they actually improve and go towards like better scores, with INLP achieving the highest scores in OSCAR a second amongst all of these different methods at removing these biases. So this tells us that we are indeed able to reduce these biases by changing the representations alone. There are, of course, other ways of trying to intervene. And as I tried to talk about earlier, like there are different ways in which we'll have to collaborate to try and reduce biases holistically overall. So this would also require the data set that we trained our task on to be more balanced. Also the data set that we trained our embeddings on, and so on. But just by changing the representations, we have been able to reduce the biases significantly. So in the next segment, we'll actually try and see how the representations change when we apply any of these different methods. So I'll hand it over to Archit Rathore now to describe the tool and tell us how to access it. So thank you.
So Sunipa, there's yeah, okay, I think Vivek answered it. All right, so let me share my screen. So the link to the tool's source code has already been put in both the Zoom chat and the Rocket chat. I would encourage you to go to the link and follow along to these instructions as to how to get this tool running on your own system. In the next section, we'll be working with the tool and going through examples. So it might be great if you can follow along with the tool on your own and test your own word sets and everything. All right, so once you get to this link, there's instructions to do the installation. Please note that this requires Python 3.x. It does not work with Python 2.7. And so with that said, the first step is to install these requirements, libraries. I already have them installed, so this goes quickly. But if you are using pip, you can use pip3 to make sure that it's using Python 3, or you can use Conda to install these library. Then what we are going to do is we're going to download this repository using the git clone command. If you do not have git installed, you can alternately go here and download the zip and extract it into a directory. The code is a bit larger because it also contains the pre-trained glove embeddings. So it's going to take a little bit of time to download, but once that is out of the way, you can go into this directory and it has a bunch of files. But the only thing that you need to do is to say Python 3 -m flask run. The same sequence of commands is also provided here in the installation section. So you can just copy and paste, except this part where you actually need to cd to the appropriate directory. And once you run this, so I had it already running, so I'll stop that so that you can run it. Once you run this, you'll find a link showing like a local server spawned in your terminal. And if you click that, this is going to open up the tool. So let me know in the chat or on Zoom if you have any questions with the installation. We'll be taking a short 15-minute scheduled break. So I would encourage you guys to try and get the tool downloaded and running. And we'll be here to provide any clarifications or support if you encounter any errors. Thank you.
Yeah, there's supposed to be some coffee and snacks outside in the lobby. So, so go and help yourself.
There is also a question in the chat, a delayed question. When modifying only subsets of words, what is the impact on the text classification or any downstream task? Do you have benchmarks numbers?
Maybe I can just quickly answer. The short answer is it does not affect things too much. So the papers have these numbers, at least on the natural language inference. The quote unquote debiased embeddings don't seem to change the performance in terms of downstream tasks on the benchmarks. We can send you paste pointers to the papers where this information is there, and you can follow up on that.
Yeah, if you're asking about, so the experiment where we did the flipping of words, I think that was mostly before we figured out how to run a bunch of these downstream benchmarks. And so I don't think we did extensive experiments on that. But I think I recalled it did not change stuff too much in the structure of the embedding. So I wouldn't expect to change too much, but I think if you flip 100% of the words he and she, there might be some tasks where it does. And this will be kind of task so specific. If you're specifically doing a co-reference task with a lot of use of the words he and she, it might have, have some trouble in that case. But in kind of general, so benchmarks, I would expect it to be pretty small. But for just the flipping experiment you saw at the very beginning of Sosanipa's section, I don't think we did detailed experiments on that.
Yeah, intrinsically, it did not change anything. So all the intrinsic tasks, which were based on similarities or analogies, we had the same scores when we did not do like 100% flip. At 100%, it did break down. So, but at 50%, for instance, if it was not like something that was like a task designed to examine a very specific gender dissociation, it would not result in any difference downstream. But for the other methods, we actually do have these numbers. I've pasted the paper in the chat where we see that there is no difference downstream.
This is an interesting point. We are officially at break, but I'm going to continue talking. Feel free to take a break and we'll come back in 15 minutes. But this is an interesting point because if we keep removing information from these embeddings, it's only natural to expect that at some point we'll destroy the embeddings. And one of the things about debiasing really is we want to find a sweet spot where we don't want to remove information that we want to keep, and at the same time we want to remove information that expresses societal stereotypes. And that's there's a bit of a sweet spot tuning that needs to happen there. Right. So for part of speech,
paper now, which
so,
actually also tries to talk about that sweet spot.
So regarding the comment in the chat, there's for tasks like part of speech, I'm not entirely sure we'll have trouble. But I think with tasks like co-reference resolution, if we remove all differences between the word he and the word she, which means that they essentially become the same point in space, there's no way to link, say, he to another mention of the word her, he to him and she to her. So that difference gets lost. So that's where the sweet spot, that's a good example of the sweet spot. But I don't know if for part of speech, this makes too much difference. We'll come back in 15 minutes. Feel free to get a coffee and cookies apparently in the hallway. I'm going to go into the hallway and look for them myself.
So I've started up the recording again in the cloud. So just so everyone knows, this is being recorded. Only the screen share and the speaker who's sharing the screens, so likeness, so will be recorded, but if you ask a question, that will be captured. You're welcome to do it in the chat or in Rocket Chat. So Achit, so why don't you take over from here?
Yeah. All right. So I hope everybody was able to install the repository and the code. Please do let us know if you want us to go through that once again. Yeah, and I'll go through it once again in case somebody missed it or we have new people. So the code's link is already in the chat. again, install the dependencies.
Archit, have you forgotten to share your screen?
Oh, sorry. Thanks for that. Yeah. So yeah, the codes link, the code link is provided in the chat. The installation instructions and the requirements are here. First, install all the required libraries, and then git clone this repository. Then go to the directory you just cloned. There's a bunch of files here, but you only need to run this command, which is also provided here. You can just copy and paste it. And this should give you a link in the terminal that you can then click on, and it will run a local server. If people are having some installation issues and are not able to get to this local server, we also have a server deployed at this link, which Sunipa is going to paste in the chat. You can go to this and follow along as well. It would be ideal if you can get it to install on your own system, since the hosted server can only host like a handful of people. But in the worst case, you can always go to this link and follow along, or you can just look at the screen share and listen to us go through the worked out examples. Let us know any questions you have in the chat, please.
The instructions that Archit just went over to access the tool, I've also pasted them in the chat, so you can just copy paste from there too to run on your own system.
So there don't seem to be any questions in the chat, and that can only mean one of two things. Everyone got it working perfectly, or people are not doing it. Excellent. Thank you so much, Jamie and Vidya. So we have it running, and now I think we're going to just step through examples. Shall we start? Archit, are you ready?
Yes.
Okay. So the first thing that we'll see is before we look into the general each of the methods, I'm just going to give you an overview of what this interface shows. So at the top, we get to pick an algorithm. So we saw 4 algorithms so far. We saw linear projection, hard debiasing, Oscar, and iterative null space projection, and all of them are available there. Let's go ahead and select linear projection. And those of you who are working on this on the side, I encourage you to follow along. And Archit's also doing what I'm saying so that you can see a version of that. Now, so we are going to now use linear projection to and step through the algorithm to see what it's doing. We'll use the subspace selection method of 2 means. There are other options, but 2 means is good enough for now. In order to do this, we need to, the subspace that we are going to select for the first example will involve the concept of gender. So we can rename concept 1 to gender so that it just shows up in the visualization. And we're going to define gender using 2 directions, or using 2 sets of words. The first set of words is let's say the male side of things. We're going to use pronouns which are definitionally gendered. So we'll use he and him. So you can type it in there. We, in general, most word lists that we provide here, except with one exception that we'll see later, are going to be comma separated lists. So you just type he, comma him. And on the female side, in the other tab, when you press tab and move to the next word set, you define it with the words she and her. So she, comma her. So what we would like to see is how does the direction defined by these 2 sets of words, the he, him, and she, her. So the mean of he and him to the mean of she and her. How does that direction visually correspond to, say, occupations? So we'll define an evaluation set of occupations. We'll use the words engineer, banker, nurse, and receptionist. Now, of course, if you feel that typing words is a pain, you can always choose our canned examples. In fact, the example that I've just talked about is the first simple example. Now, at this point, we're ready to see the thing. You can click run, and you'll see that the visualization opens up 3 different panes. On the left side of things, it's called initial embedding. This pane shows the original a 2D projection of the underlying of the word embeddings as they are, and it also shows this gender direction. It's just the gender vector that's highlighted on the screen right now is just a unit vector that points from the she, her words, the mean of those 2 words, to the mean of he and him. And it's centered at the origin so that we have a fixed point that stays fixed through the whole process. And on the right-hand side, the far right, we have the result of debiasing, and we'll get there. In the middle pane is where we'll go through each step. Just as a reminder, through this entire demo, for this tutorial at least, we'll be using 50-dimensional glove embeddings. But there are instructions on the Git repository for changing, swapping this out with other embeddings that you want. You can do that offline if you want. So in the intermediate thing, we're going to step through the process. So first, if you see these arrows in the bottom, so if you click forward, just 1 step forward, the first thing we'll see is a reorientation of the camera or of the view. Nothing has changed in the underlying embeddings themselves, but just the view is reoriented so that the gender axis, the line, the direction that corresponds to gender is the horizontal axis on your screen. And now we see something interesting. Let's maybe step through what are the various things we see. First, notice that the gender clearly, actually, can you go back? Yeah, so the gender clearly goes from the orange points, which we have defined to be the female side of things, to the green points, which are the male side of things. So he and him. Now, this is just the definition. But however, notice also that let's look at the occupation words. There's something interesting. If you draw a line through the origin, separating the he, him, and the she, her, you'll see that receptionist and nurse falls on the female side, and banker and engineer fall on the male side. This illustrates the fact that these embeddings encode this stereotype that the engineer and banker are male jobs, however you want to define it, and receptionist and nurse are female. We would like to remove this bias. So you can now click forward in the demo, and it'll now we are applying the linear projection. What we are doing is we're just saying remove this component, the gender component, from every word in the embeddings. We only have 8 words here, and so it's removing it from all 8 words. In fact, in the actual thing, every word in the entire embedding, this operation will be performed to the entire set of word embeddings. The nice thing about this tutorial is you can see, you can go back and forth, as I showed before, but we can do it again. The original words had this clear difference between the male and the female words and the occupations, and now we are essentially merging them. What has happened here? Remember that we are working in 50 dimensions, and what we see on the screen is just a 2-dimensional projection of these words. One of those dimensions was the gender, and we removed that. We are left with 49 other dimensions, but only one more dimension is shown on the screen, and that's the vertical axis. We see that all the words have essentially are lying on a line along the vertical axis. There are 48 other dimensions left. So in order to see how, or 48 other components left, the embeddings are still in a 50-dimensional thing. There are 48 other independent components left. We can reorient our camera again in this 50-dimensional space and project once more. You can, if you step forward, we'll see the reoriented view, and that's the debiased embedding. What we notice is that what we originally defined to be gender, the direction of gender, has now collapsed to the origin. Essentially, that component of information has been removed. As a result, on the left side of this chart, we'll see that the words he, him, and she and her there is no way to separate the green points from the orange points with just a line, for example. And what we see on the occupational words are really just the remaining words after this particular operation has been performed. Just a last thing I want to say before moving on is, on the initial side and the debias side, the tool allows you to zoom in and out of the words. It may look like the words are clustered, but you can use your mouse wheel to scroll and zoom in and out to see the points more clearly. All right, this is all I have to say about linear projection, and now we can move on to the other methods. You want to take over?
Yeah. So we just saw how linear projection changes the space, and so the next one that we want to go through is that of hard debiasing. Let's first choose the algorithm there to be hard debiasing. Now, if you recall, the primary difference between hard debiasing and linear projection is that hard debiasing first categorizes its words into different groups of what to debias and what not to debias, and like what to equalize. So I'll go through this sequentially. So let's still keep it to be gender that we are trying to find the bias along and debias. Now let's keep the method we use to choose our subspace also to means. So here, like Vivek pointed out, we need two groups of words, one male, one female. One thing to note is that these don't have to be balanced. Like they don't have to be like paired words like he, she, man, woman, or something. And they don't even have to be equal in number. Like we could have 10 words in one and like 6 words in the other, for instance, because we're just taking a mean anyhow. So just to emphasize that, let's say we put in a word extra in the male group, let's put in man. And let's keep the female word set as is. So this will essentially find the two means of the two groups of words and use them to find the direction of bias. Now, in addition, we also need one more thing is, since we are using these words to define our subspace, as we recall, like these words are the ones which will not be debiased. So they'll be left as is in the embedding space. We won't like do any projection or any step to them, which will try to take away any component from their embedding. Now, the next step is to determine the equalized set. So these are pairs of words, which it first debiases the projection and then reintroduces like some amount of gender component into them in a very controlled way so that they're equal and opposite along this axis. So the format we have used here to put these words in, they'll be separated by hyphen. So like say himself dash hyphen, or like dash herself is a pair of words. So this is a pair of words that will be equalized, and we will put them in this format. And we might want to do this for more than just one set of words. So each set of or pair of words will be separated by a comma. So let's put in boy, girl. The convention we have used is that we'll have the male word dash the female word in this specific case, but you could always change that. Like this doesn't really change much in the space itself. It's just the convention of putting in the words, not that this is affecting the underlying process in any way. Then we also have this evaluation set where we want to see if there is bias encoded with this subspace with respect to these words, and if this method is able to reduce that. So let's keep that as occupation still. Let's keep that as this set of words. Now let's run it with this setting and see what does the space look like. So if we scroll into the first frame, we see that there indeed is some association that we can see. So all the male words are towards one side, and we see how banker and engineer are close to them, whereas the female words on the other side have receptionist and nurse. So it's still not as clear because there's just a 2D PCA projection. So the space does not really, like the frame of reference, our frame of viewing, the viewing plane is not actually very useful in understanding what this looks like. So let's go to the next step where we try to align this direction with the x-axis so that we have a better idea of like what sort of associations are there and what biases are being encoded. So here it becomes even clearer. So we actually see that there is a direction between like the female to the male words. And that direction doesn't just encode the difference in gender, but also a difference in sort of these associations with different occupations. So nurse and receptionist are far towards the female side, and banker and engineer are closer to the male side. So let's go to the first step of trying to debias this. It's similar to what we did with linear projection. So we remove the component of bias from all of the words in the space, except for the words that we have used to define the subspace of bias, which is that of gender. So the words that we had put in at the top, like he, him, man, she, and her, these are the ones that have not changed in space. They've remained exactly the same as before, but everything else, their component along this direction has been removed. The next step is now to reintroduce gender very carefully into those paired words. So if we just step through that, we see how now they have like some introduction has been done of like gender into these words, and they're equal and opposite along this gender axis. So what this aids in doing with like, if we compare with respect to linear projection, is that these words have still retained some meaningful associations, like her, herself, she, they're still forming a cluster on this side, as are the words on the male side with like he, she, and himself still being close to each other. But their associations with those occupations, they have now been like, they're not as pronouncedly preferential as before. So if you just go to the final space now to see what this looks like, and this is again a 50-dimensional space that we projected down to 2 dimensions. So here we see that if we just compare the last and the first frame, we see how much we've been able to like reduce the kind of associations that were there previously. So before there was a clear like segregation of these occupations. If we just tried to cluster the different gendered words, we would find these occupations also belonging to those differently gendered clusters or classes, but that's not quite true anymore in this debias setting. So this is how hard debiasing changes the space to reduce the bias, but also in a very controlled way, try to retain some meaningful information using predetermined word lists. So this is all for this method, and let's move on to the next methods now.
So now we're going to talk about this. So this third method. So-called the iterative null space projection, IN. So SP or INLP if it's and so in this method is probably the one that is probably the hardest to kind of understand within this visual system. It relies kind of in a number of ways on much larger word sets, and kind of how it runs in the paper and in the paper where it was proposed in like 300 dimensions is different than the 50 dimensions we have here. But let's go through it anyways. So as I was saying, this one, as Sandeep had explained earlier, this one works by trying to find a classification based, so it's gender subspace. And so we'll find a classifier and take the normal of that, of a linear classifier is defining this constant subspace. We're going to again work with gender to try and define this, but this one uses a we'll need to use a larger word set to see what's going on here. And so we'll start again with he, him, and so man. But let's change it. Just make sure I have the example right. So he, his, man. So boy, grandpa. So uncle, and then I'm going to throw a statistically gendered name in there as well, Jack. Sure, okay, and then we'll do so similar on the female side. We'll do she, her, so woman, so girl, so grandma, aunt, and Jill. Great, and then for the evaluation set, let's simplify this a little bit to just engineer and homemaker. Great, so let's see what happens. Okay, so in the first view on the left, we're seeing the view in the first principal component. or first two principal components of these words we're seeing from the 50-dimensional space. We see two-dimensional view. And you can kind of see that there's this green to orange so direction from the male from the male to female words. And you'll see I threw Jack and Jill in there. They have the same sort of direction between them, but these are kind of spread out a little bit different than the, so definitely, so gendered terms what we saw earlier. Okay, so let's go through the first step. Where let's step forward and see what happens. We're finding the linear classifier in the 50-dimensional space, and it shows the normal direction of this. And this does not quite, as you see it here, does not quite classify the green and the orange points apart, but that's because this is a effectively 49-dimensional subspace, this dashed line, which is the classifier separator boundary. And we're just seeing the two-dimensional or the one-dimensional piece of that as it intersects the two-dimensional plane we're viewing. So let's click one step forward. What this does is it reorients the view so that the that x-axis is going to be exactly the normal direction, and then we're going to have that the y-axis is going to be the best PCA component, which is so orthogonal to that. We're projecting all the points and seeing where the classifier cuts through there. This will not always even show the right separator if that's there. It's not guaranteed. The oh yeah, so it should be orthogonal. So this, if there's a separator, it should be able to show it here. So okay, and now we have all of the green words classified, separated, linearly separate from the orange words. As you see, engineer, this stereotypical male profession is on the left, and homemaker, the stereotypical female profession, is going to be on the right. Now Jack and Jill are right in the mix with the other words in this case. So okay, so now we can do the, and we haven't done any changing to the embeddings yet, and we'll do that in the next step. This is kind of this linear projection step along this axis. Okay, and so so now we see everything has been come down to this 49-dimensional subspace, and as we do one step forward, we'll see this again in the view of PCA of this space. So again, we have these 49 kind of dimensions where the data lies, and we found the best two-dimensional representation. And so now you can see that and a bunch of the words are mixed up. Still, Jack is lower than Jill, and that's similar with some of the words on the left, like boy and girl, but grandma and grandpa and aunt and uncle are opposite. So there's not this clear correlation anymore. But so what this INLP method is based on is that there might still be some residual information that's allowing you to detect some gender information. So we might be able to find another classifier which can still, maybe not perfectly separate these points, but find some sort of correlation. Okay, and so let's take another step forward, and it keeps iterating until it can't anymore. And our viz will always do at least 2 steps, so you get a sense of this. And this is another direction it found. Okay, and let's do another step to reorient it so we can see what it's doing. Okay, and so the best one it found in this case was something simple. It separated Jack from Jill. It says Jill is pointing towards this direction, and there might be other connotations based on what the loss function is scoring stuff, but this one is capturing perhaps some residual gender information in how the words are distributed. And so then we can apply this iterative projection again, and this again maps it down to another dimension. These directions should be orthogonal with each other. In the way this technique is formally defined, that it forces that they're orthogonal. So we're now down to a 48-dimensional space where all of this stuff lives. And based on the question in the chat, this is reducing. It's always still a 50-dimensional embedding. The representation of the data is still 50-dimensional. That's how it's stored internally, but it's on a 48-dimensional subspace after 2 steps. In the paper they recommend, or their code I think says, does 35 iterations, right? So in a a 50-dimensional space that gets you down to 15, that's probably too many. But in a 300-dimensional space, that might not be too bad. Okay, so it keeps reducing down the subspace, the linear subspace that all the data lies on, and this is the final PCA view. Our visualization will keep going if there is something that the classifier can do something meaningful. Otherwise, it will stop after 2 iterations. Things get unstable and weird after that, especially with small data sets. Okay, so now you can see stuff is even more jumbled. There's even less of a correlation between these sort of things, and they're spread out even more. So we've tried to get rid of as much of the gender information as we can. So before we finish this, I again want to reiterate, this is not exactly capturing what the paper is doing. It starts out with the seed set, and it uses that to find words which are similar to those, basically a constant fraction of the words, and then it tries to classify that constant fraction. And this gives it much more to work with, and why it makes sense to run more directions, but it does not need to seed it with 10,000 words. It seeds it with some smaller number, and then it kind of extrapolates to get more words to try and classify here.
Hey Jeff, there's a question. In this method,
so I answered that already. Yeah. So
okay.
Yeah. So great. But are there any other questions about this? Yeah. So go and try, put in different words, and so see what happens. Yeah. So. But after this, we're going to move on to the last method, and then we'll go through a couple of some more interesting examples that we've picked out. So the last kind of algorithm we've implemented within here is this Oscar algorithm, this orthogonal subspace correction and rectification. And this one is doing something fairly different than the other 3, and that's not trying to project out information. It's not effectively reducing the dimensionality of the data along one or more subspaces or part of the data, but it's kind of trying to instead, it's keeping the full dimensional representation of everything the whole time, but it's trying to make concepts orthogonal to each other. So for this one, we're going to do, this one works better using PCA instead of 2 means, because it's trying to find subspaces specifically. And so PCA method is capturing the most representative single one-dimensional subspace on a set of words here. Okay, and we're going to again go back to the most common kind of application of gender as the first concept subspace and occupation as the second one. We're going to need, instead of just having a list of words, we're going to actually identify a subspace. For gender, we're going to, and because we're using PCA, we put them all in the same bucket. It doesn't distinguish kind of some binary notion of gender in this case. We can use the words, so let's see, so he, so man, boy, him, okay, she, we'll put some female words, so woman, girl, and her. And then we'll put some occupations in the occupation set. We'll use, so scientist, so doctor, so nurse, and so secretary. Okay, and then there's an evaluation set which won't determine the algorithm, but we'll just get to see how words move. We'll use, so we'll keep engineer in there as an occupation, but I'll also put in a couple of gendered words. So we'll use, so tiger and so tigress. Okay, these will be a good example of what's going on here. Sure, okay, so what we see here is now we don't have 2 types of definitionally gendered words, we just have them in green, and then the occupation words are in pink. And another occupation word, engineer, is mixed in with the other pink words, but that one is purple, it won't influence the algorithm, and tiger and tigress are in here as well. Okay, and so now we've identified not just a single subspace for gender, but one for gender and for occupation. these were PCA vectors and then translated so they are at the origin, and the sign here is arbitrary on these. So they could have pointed through the words, but this was an arbitrary choice. Okay, to see a little bit better what's going on, let's step forward. And what this is doing is it's orienting first the gender direction again on the x-axis. But now the y-axis is not chosen by the PCA of the remaining values of the words. It's chosen so that we see exactly the span of these two vectors, gender and occupation, right? So you can do like a small, small version of Gram-Schmidt to kind of find the two orthogonal components, and that defines this two-dimensional subspace. Okay, and so we're seeing exactly the components defined by these two concepts that we found the span of them. And we can see that the gendered words in green find this pretty nice horizontal line here that we found. And this is exactly horizontal because we've oriented the gender direction along the x-axis here. All right, and then we see that there's kind of a subspace that goes through these occupation words, and this is kind of angled up. It's kind of correlated. It's in the same, somewhat the same dimension as these. So as these this stereotypical gendered words, and as we see that tiger and so tigress, which captures the gender of the tiger, I guess, is they're lined up, they're horizontal as well. Okay, so that's a kind of what we expect to see here. So all right, so now let's go through and do we haven't changed representation yet, but we're about to do that in the next step here. Okay, and let's step forward. And now this is a kind of a smooth graded rotation of the space. And what you can first most clearly see is that the gender and the occupation axes that we identified are now completely orthogonal to each other in the span. We only changed data in the span. The other 48 or 298 dimensions have stayed exactly the same. Those components have not changed for the vectors. So, okay. The next thing we see is that those gendered words are still horizontally aligned. They were close to the horizontal x-axis, so they basically stay as they are. Okay, and then we can look at the occupation words. They were kind of in a subspace on an angle correlated with gender. We've now kind of smoothly rotated them up so that they're now so vertically aligned, right? If you were to find a subspace through them, it would be vertical at this point. And this is common that the gender words are much more clearly defined a subspace than these than the occupation words or a lot of other sort of subspace you try and find. You can find them, but they're not as cleanly defined as the gender subspace. That's probably why most papers may only focus on gender or mostly focus on gender in these sort of things. There's signal in these other ones, but they're a bit, it's not as clean. Sure. So okay. So now the next thing to notice is that the word engineer, this was not used to define the algorithm or the transformation, but it has moved with these other points. This operation is applied to all the points in the data set. So because it's in this occupation cluster, it's moving with that in this graded rotation of the space. Okay, so it's remained with these occupations. So we have not tried to remove an aspect of gender in this case, but what we've tried to do is make sure that the components are orthogonal to each other. So there's not a correlation between them. We've not defined a male and female side of this. We just said there may be a correlation, but we've tried to remove that so that the component of the space that captures occupations and captures gender should not basically have correlation with each other, and was left over, might be meaningful, it might end up being noise, but this is trying to go back to this non-distributed representation of vectors with these one-hot encodings. In this rotational view of the space, the horizontal component captures the gender dimension, and the vertical one captures the occupation dimension after we've done this rectification. The other 48 can be used for something else. So the final thing to point out is that we still have this gender direction here. And so this might be a little bit more clear so we can zoom in. So let's take one more step. Let's take one more step to get the PCA view. We can see that now it's no longer the horizontal axis, but we still see the gender component in this view. What's nice about the left and the right frames is by scrolling, you can zoom in on these. Okay, and so we zoom in, we see that, okay, the male words tend to be on the upper part of this axis, he, him, and then there's she that's there, but that's below him, right? We didn't use this two means approach, we used the PCA approach. So they're jumbled, but they kind of definitely give this directionality. And so the female words tend to be at the bottom. And now if we look at tiger so tigress, tiger is the male version, and that's in this along the axis on the male side. Okay, so we've retained this gender information. We haven't removed the gender information from any of the words except for the ones along the occupation subspace, which we've effectively rectified, but we've retained it for the other words that have this component. Their variation off this is not along this occupation subspace, but along these other subspaces that may capture some animalness or something of the words, but the gender component of that is still retained. So that's one of the powers of Oscar. So great. So any general questions about this? I think maybe we'll go through another Oscar example. Now I think we'll. So this is the general algorithms. We're now going to run through a few other examples. I think I was going to do the one with Oscar and so names next. So let's. Yeah, you can jump right to the 13th example here. Okay, and I think the only thing I've changed here pretty much is I've changed the occupation subspace now to be a bunch of names, which are statistically gendered, usually often in a binary sense with gender. And so we may want to remove this. We may have someone's name in some NLP context, and we don't want to correlate that with gender, for instance, with some resume sorting. For instance, there was this issue with ethnicity I showed earlier, where you had people with a black correlated name would tend to get these ads for things like, what arrests that they have. And you'd want to possibly remove this from the connotation of names. Can we do this with gender? And this is something that will show up in a nice example here. Okay, so let's, you can kind of see the two clusters. They're fairly well correlated. Let's step forward one here. So again, now we have gender on the x-axis and names as this kind of, if you extended that, it would go through the pink cloud of points that captures all these names, that names axis, and the sign flip is arbitrary here. And so you see these are fairly well correlated with each other. So there's a fairly small angle in them with respect to, if you put in like cat or something, it'd be quite different. And so we'd like to uncorrelate these things. And so let's see what happens when we step forward with Oscar here. What happens is, again, we orthogonalize this names component. So this becomes the y-axis. And then the names are kind of spread out more along in this vertical direction, and they've also been kind of rotated down, so they're away from the origin. So now this kind of correlation between names and gender is so something that can be kind of rectified in these word vector embeddings if you choose to do so, right? You don't have to do this, but you might have applications where you would like to kind of remove or orthogonalize this kind of correlation between these names and these definitionally gendered aspects. Great. So any questions with this example? I encourage you to go and play with some stuff yourself. There's some of it is a little sensitive. If you change some words, it changes the sign of things and stuff, flips around a bit, but kind of the general principle should still hold. I think there's
And
gonna be
one other comment. I had a comment. If you
go
have
ahead.
examples that you try that look interesting, please share with us. Because in some sense, one of the uses of these kinds of tools is it allows us to explore these ideas, right? So we would be interested in any interesting examples that you encounter as well. You can share with us through the chat or just email us if you want.
So Vivek, I think you were going to go through one of the examples with, oh, so there's a question. Yeah. What about binary concepts that are more, or that so that are more than binary, like race, black, white, Indian, and so names. Yeah. So these are, so how we just go into the next example we had planned. They'll give a taste of this, and then maybe we have some stuff we'll say more as well.
There's another example also, correlation of jobs to national origin, for example.
Yeah. So we've explored some of these, but not all of these. So I encourage you to try this with PCA method for determining the subspace. It does not require a pairing or a binary notion of them. So you should be able to type in a bunch of words you think are representative of that concept, and hopefully it will capture them. There's in the AAAI paper from last year we cited, it looks at trying to do this for some concepts of religion.
We have an example here, right?
Yeah, why don't we show an example here?
Yeah, great. So go ahead, Vivek. Why don't you take over?
One thing is that these points are actually, so we've determined subspace using a PCA here. So actually, even though we've used words of a binary nature, we haven't used a binary concept determination method. And this makes it more generalizable to like concepts in general, like gender in general, or say nationalities in general, where we choose words in a way and we do a PCA on them so that we get a general concept. And there's some preloaded examples here. Yeah, sure.
There's another point actually in Jamie's question. Concepts that are more than binary, like race and names and say jobs and countries, most of these methods essentially involve identifying a direction or a subspace. Now, if these concepts are more than binary, then the standard thing that's done is you identify the principal component, the most dominant direction among these words. And I think, Sunipa, you wanted to go over an example with the nationality, right?
Yes, I can quickly go over another example, like which actually does not look at gender, for instance. And so let's just do, let's choose nationality case 1 with linear projection. So this one has actually used a binary aspect, but the other case there uses a PCA over all of these different concepts. We can go through both as well if there is time. So here we see we've used these words like Syrian and Persian in one group and American and Canadian in the other group. So if there was no direction, we wouldn't have seen this sort of clear like difference between them. So for instance, if let's say we disable the concept direction. So we can toggle that at the bottom. So let's say we disable that and we even take out the evaluation points, for instance. Even then we can see that these distinctly form two different groups, like American and Canadian are there in one group far away from the other two countries. So if we enable the direction now and the points, we see that this not only encodes a difference in these nationality groups, but also in these sentiments associated with them. So if we zoom in, we can see how like cunning and greedy are on the Persian and Syrian side, whereas good and smart, they're on the American and Canadian side. So these are very pernicious issues and it's extremely problematic, and we should not be actually having these in our representations when they could be making very important decisions. So trying to remove this using a method like linear projection, what it would do is it would remove this nationality difference. So let's step through that and see if that actually helps this issue somewhat. Now this is just aligning it with the x-axis. The next step is to remove the components of all these points along this difference in the nationality groups. So in the final frame that we have, these different nationalities now no longer are in like a different group. So if we just go to the next step now. So this is basically the final frame. What we see here is that if we compare with the initial frame, the two groups of nationalities are now merged. They're no longer in those two distinct groups, or like they no longer have that direction which was encoding this bias. So we are able to like mitigate this bias to some extent and dampen it in these representations. And the associations are also no longer like as pronounced as before in their biases. So this is one example. We can also try doing this in a more general way. Let's just do the second case, where instead of doing a binary way, we're just taking the PCA of the different, like we've taken a group of like nationalities, and we basically want to see like, if we just do a PCA on it, does this also define a similar axis? Here too, if we remove the like the direction now and the evaluation points, we still see that there still is this sort of direction still remaining. We haven't done that binary sort of grouping. And if we enable the direction and the evaluation points, we see like similar associations here too. Like these points are associated differently to these different countries and or nationalities, and we are able to mitigate them in a very similar way when we try to take away the nationality direction by linear projection. So the results are very similar to what we see with when we did a two means approach to find the direction as opposed to PCA. It's just that we have not used like two groups, rather we've just used nationalities in general to get like a concept subspace for nationalities. So we've had like in like some of the papers we've cited in the slides and also on the website page, we've actually done this for like different kinds of biases, like age-related biases or nationality and religion-related biases. And in all of these, we've seen improvements when we actually try and identify these directions and use any of these different mitigation methods to dampen the bias. And the best thing is, like we discussed before, these are all post-processing approaches. So we're able to mitigate without adding to the time or the complexity of getting these representations.
So I think we have time maybe. So Vivek, do you want to show one more example? I think this is more fun than the slides we have planned.
Yeah, I like the royalty.
This is the thing. I mean, we have about 30 minutes, 25 minutes left. And
we have like 40 minutes left.
We have 40 minutes left. Yeah. Okay, so we can walk through one more example and then go back to show,
and I'll go through an example in the part on critiques.
Okay, well, so let's do this royalty example. So here, the question really is, are royal people better than common people? And if we don't believe that, can we remove that, or can we remove that idea from embeddings? Or equivalently, can we introduce this sort of a norm using the context of normative reasoning? Can we introduce this norm that royalty is no better than you and me, assuming that nobody in this audience is royalty? So as an example, maybe can you, Archit, can you use linear projection? And for the two means, select the two means example, a two means subspace method, and and rename nationality to say royalty. And on the first set of words would be words that are definitionally royal. So let's say king, queen, prince, and princess. And the second set of words are definitionally not royal, almost. So let's say we have man, woman, boy, and girl. And the evaluation set would involve just two words that express sentiment. Let's say we wanted to see which side is great and which side is mediocre. So great and mediocre. Okay, so now if you click run, you'll see that the initial embedding, there's a clear separation between the green points and the orange points. The royalty is one side and the common folk are on the other side. But let's reorient the view by stepping forward one step to make this difference very clear. This clearly the line that's called royalty points towards, well, the royalty. But also we see that if great lies more on the royalty side of things and mediocre lies more on the common side of things. And this is the kind of thing that we want to remove. If you step forward one step, we will smoosh all the words together onto the vertical axis here. And essentially what's happening now is we are not in, there's no correlation between this royalty axis and the axis that defines great and mediocre. And if you step one more forward, we get to the final view, which is the same as the debiased embedding. We see that first of all, there's no single direction that points from, say, common to royalty. So if you look at the points girl and princess and you connect them, it points down, but man to king points up. So there's no single royalty direction, at least as far as these 8 words are concerned. And because there's no royalty direction, there's no correlation between that and this direction of great and mediocre. This is just a toy example. This is just a fun example that we can use to kind of answer this question or to point out that it's not just gender bias. In some sense, anytime we are using a debiasing algorithm, we are introducing some sort of a norm that we believe should exist. And this is the kind of information that we want to inject into our word embeddings. I think this point that I just made probably leads into the discussion, right, Jeff? So we should probably go there.
Yeah, so I'm going to
there's
switch
a
over
comment.
to.
There's a comment. However, a great is still closer to king, man, prince, and mediocre is closer to queen, girl, and princess. That's so fantastic that you point that out. That's another bias. That's a gender bias, which is in some sense additionally there, in addition to what we might call royalty bias. So that
also,
means that
some
we need
age bias in there as
there's
well.
also some right. So
there's a concept of intersectional biases when there are more than one bias, when there's more than one bias in play, and then in the intersection of these biases, there is a greater effect than compounding. So that is a whole other way, or like whole other problem in itself, when there are multiple biases in play.
And there's a common question, right? Can you mitigate royalty, gender together? Well, to be honest, I don't know of any work that talks about this in the literature. But one possibly naive way of doing this is first you remove the royalty axis component, and then you define a gender component, and then you remove that also. Of course, there's a question of what's the order in which you do that, and does that affect things? Which algorithm should you do? How many steps should you do? Should you do INLP? These are all fantastic research questions, and I think you should think about these things.
Yeah, great. So I think all these are great questions. Well, I'll prepared a couple slides to go through some of these, and at one point we'll jump back into the demo. But at this point, maybe you can stop sharing, Achit, and I'll jump back to some slides for so a bit here. Okay, so now you should be seeing my screen. Yeah, and we'll talk about some critiques or kind of on these word vector embeddings, so bias removal, again, kind of back to stuff we've been talking about, which bias should we remove? Part of this question is, should we only do gender, or there's these other notions of possibly royalty having to do with regions of the world, having to do with age, that shows up in this. Again, the majority of the work has been focusing on, in fact, a binary view of gender. And so that shows up partially because I mentioned it's a very clear signal, right? There's a signal to noise issue. It's harder to kind of quantify in these downstream tasks, these other things, but they do actually show up. Right, and there are a number of categories such as gender, ethnicity, so religion, sexual orientation, and and other ones that there's actually, at least depends on the country, but definitely in the U.S. there are laws that protect against these within, say, hiring practices or I guess admissions into So like loans and stuff like that, where these need to be protected within some sort of use case, right? So if you're doing for that sort of task, you might, that would be a good indication. You might want to try and remove information from all of these if you're using some NLP approach, which is probably using some of these word vector embeddings in some way. Yeah, again, I mentioned the signal is much stronger for gender than these other ones, but you can find it. And the PCA approach does not require some binary notion. It could be multidimensional, and a lot of these techniques have been defined so that we didn't implement them in the visualization, but they've been defined so they can extend to multiple dimensions. Subspaces, other ones that hasn't been explored as much, like an Oscar, for instance. Sure. So there's another question that's come up. Is there still some residual bias, right? And I'm going to kind of address this in two different points. But there's this paper by Goldman and Goldberg from NACLA 2019 that argued that these bias methods leave behind some sort of residual bias that you can still find, and it can be relearned from the data. They particularly studied the hard debiasing approach. And so I think to illustrate this, I'm actually going to quickly jump back to the visualization. So Acha, if you can share your screen again. Oh wait, I did that the wrong way. So Acha, if you can share your screen again, that would be great. Great. So if you can load the example lipstick on a pig. So hard debiasing, lipstick on a pig appeared in the title of their paper. And so what you can see going on here is that this is an example. The examples they use in their paper again are going to be much larger, and they show this in some more kind of sort of rigorous set. I've used examples from their evaluation set, which is smaller. It doesn't quite fit, but it'll illustrate what's going on. I've used as a gender notion, he and she as the to define the gender axis, and then an equalized set. This is in their one of their evaluations. It used names, and I'm just showing what happens with these names. I paired them up arbitrarily between statistically male and statistically female names here. And then in the evaluation set, which the things we're trying to explicitly remove the gender connotation from here, I have some occupations. Okay, so if you step forward through this, Achet, you'll see how we kind of this view where gender is on the x-axis, and these are kind of scrunched up in this other dimension, but it's got the same kind of gender stereotypes that we had seen before. Okay, and then if you step forward on this, you'll see that it's everything but he, she. It projects, and then you make another step, and it pushes back out the equalized set, which in this case is the names. Okay, and that's a little bit scrunched up here. So let's go to the PCA view of what's going on. It pretty much retains stuff, but we can see it a little bit more clearly in this case. Okay, and so what the main thing that this paper points out is that the words homemaker and receptionist are more clustered together. We were supposed to remove the gender component of this, and as we defined it with the he, she direction, and as is correlated with names, the gendered associated names, that has been removed. But homemaker and receptionist are close together, and so engineer and lawyer are very close together. So for instance, if you knew that homemaker was a stereotypically female occupation, then you could gather from that receptionist is going to be as well. And similar between the lawyer and the engineer. You can gather this because those words still tend to cluster together. And so the main example was pointing this out with these occupation words, which you tried to debias, but you'll notice that this is also true in the equalized set with names. That is also some residual bias there as well. And so these components which are left in the embeddings allow you perhaps to try and relearn this gendered information in these associations. So let's go see what happens with linear projection, and we'll see where this carries over in some way as well. So let's switch the example to lipstick on the pig, linear projection, and I've removed the equalized set because those don't exist anymore. Those will be projected just like these evaluation set. And if we step through this, we'll see that it's the same occupations. There's this stereotypical male parts encoded. And once we project them, okay, we still have this clustering between receptionist and so homemaker and engineer and lawyer. That's still there. The he and she points are now directly on top of each other, right? So there's no longer a he, she axis anymore, but there's still the clustering of these terms. So you could potentially relearn this, but you can't necessarily use the pronouns that have been used to try and learn this direction. And any associated programs like pronouns like man and woman also would have been compressed in this way. So with the linear projection. So there's less residual leftover information from this stuff in this linear projection approach. But based on this clustering approach, it might still be there. Sure. This kind of concern has been raised. In fact, the authors of this lipstick on the pig paper were some of the authors on this iterative null space, linear projection approach. And so let's look at that, a similar example with that approach. Okay, and here I've again. This is again kind of a guess of what it's doing on a much larger data set. But now it said, well, let's say we know he and she are going to be gendered, but we also knew engineer and banker are stereotypically male gender, and nurse and receptionist are. But in the evaluation set, we want to see how this generalizes to doctor and maid, which either we don't know or we don't want to use in the training aspect. Okay, so let's step forward this algorithm. What it does is it finds a nice separator between the ones we've encoded as male and the ones we've encoded as female. If you rotate this, we can see it better. Okay, and this correlation is still there. So doctor's on the other side, but it's towards the male side there. So that may still be present. Let's step forward now, and then as we project, we've kind of all the stuff we know information about has been kind of, the bias has been removed. If you do one more step in the PCA view, you can see what happened. Essentially, it's basically paired each of the green words with one of the orange words, and there's really not much left you can see. If you run it in the algorithm, it'll learn something, but you can see there's not much signal left among these words, and you can iteratively keep classifying this until you've removed, for all the data you have labeled as gendered, or you can infer as being gendered. You can keep iteratively doing this until you've removed this information. Great. So that's kind of just a visualization of this critique. Great. So kind of any general questions on that? Otherwise, I'll jump back to my my slides and go through a couple of other critiques correspond with some stuff that has been mentioned in the questions. Yeah, so let's go back to this. Okay. Great. So hopefully you're seeing my screen again. And so this was one critique of the residual bias, that there's still some that can be relearned here. Another way of thinking about this is by looking at these kind of quantitative ways you can measure it. This was not so much a quantitative way. Otherwise you could learn it with the classifier, although they've identified this through clustering more or less. But the other way of thinking about this is when we compute these weight scores or these net neutral scores, they're not exactly showing 0 amounts of bias. The weight score does not go all the way to 0. It's reduced significantly, but it does not go to 0. The net neutral score does not go to 1, saying it's completely so neutral after we do these things. And should this be concerning? Well, if you remember from the first part of the tutorial, this bias enters the pipeline that we're using to do these things in multiple different ways. One is the data and the representation. But when we're doing this evaluation through natural language inference, we're using this this existing approach, which is trained on this SNLI. So training data set, and that itself may be encoding some gendered information, some biased information into it, right? And that part we're not working on, so removing. There might be other ways of doing that, but we haven't explored that. So that's a kind of we can show it's reduced, but the fact we didn't get it to go all the way down to 0, to show there's no bias remaining is possibly expected, right? And with the weight score, we've asked on the weight score is actually on a pretty small subset of words that is being used, and those words may kind of have some various sort of connotation to them. If we have a larger set, maybe it's going to go closer to 0, but these are things that haven't totally been explored. And so there might be other factors involved here. Another way of thinking about this is that in certain mathematical ways, depending on how you define the representation of bias, it has been removed, right? If you think about the way to represent bias is to take the mean of both of these sort of these two subsets of binarily stereotyped words, and then you want to make so those means are equalized, and this is what like this ECT score evaluates. Well, then this linear projection approach exactly does that. Those means are exactly the same spot, so the ECT score, the relative distance between them will be exactly the same, right? If your goal is to show that on the words that you have labels for, you cannot find like say a linear classifier among these words in this embedding space, well, then the iterative null space projection keeps removing anything it learns until it can't find anything left. So in that sense, is removed it from that space, right? If you think of, I don't want to remove the information, but I want to kind of ensure that there's not a correlation between these concepts, right? And I kind of want to give them kind of these orthogonal representations. Then this Oscar approach, its result is to identify the best representation of these concepts and force them to be orthogonal. You could learn something so the two extremes of 2 dimensions are classified the same way as the other extremes, but you would have to train it to do that. Otherwise, that effect would not really generalize well. That would be within kind of the noisy parts of this data and would be more susceptible to the noise that is very present in these embeddings. So in some sense, it is gone. In other senses, it might still remain, and it has to do with how you measure it. And we've only focused on this embedding, as I've mentioned before. This is such a common, essential ingredient in most of natural language processing now. It's worth focusing on just this aspect and saying, what can we do about this particular part of the representation? So okay, so another kind of critique of this is that pertinent gendered information is lost when we do these things, right? The one that is most aggressive at removing the kind of the learnability of these concepts, this INLP approach, it's removing the most information too. It's compressing the dimensionality that the data lies in, and it might remove this gendered information. So what we might want to know is someone brought up in the chat that she is female and he is male, and if that doesn't come across, then we've lost some information we otherwise knew. For instance, there could be these code reference tasks where you're given like a short paragraph, and you're something like grandma and grandpa walked in, she was glorious, so he was grumpy. If you read this, you know grandpa was the grumpy one and grandma was the glorious one. But if you remove the notion that he refers to, that grandpa refers to a male person, and so he would be grandpa and she would be grandma, then you would no longer know this, right? This kind of task you would no longer so be able to do. Unless maybe there's a correlation with grandpas who are grumpy, but it would at least make it much more challenging. So, and in fact, you can kind of plot this. This is these, think of these placements as not exact. They're subject to how you measure it again. But think of the stereotypical, the x-axis is the stereotypical associations removed, right? And so we're able to remove the INLP approach is the most kind of aggressive in removing these representations, and that removes the most. It's furthest to the right, whereas the baseline is without doing any modification. It removes the least. It doesn't remove any. But then you could think of the information that's retained about the gender information. The baseline, without doing anything, retains the most again. And you would think INLP would probably lose the most of this information, where Oscar would try and keep the most. It's not all the way at baseline, but it's the most out of all these. In these experiments, how we measured the hard to biasing tended to perform the worst in these things. But these points move around, depends on how you measure. This general pattern is there. As you noticed, we would really like something in the upper right corner where we've been able to retain all of the gendered information and remove the stereotypes that we're trying to remove. And so there's work to be done here, right? There's some steps in the direction, but this is not a completely solved problem. This is derived from, I think, one of the tables you saw earlier on glove. So one of the other things that was discussed earlier, I'll just mention this quickly. Why not retrain these embeddings, right? If I know there's this work with gender so neutral glove that actually tried to retrain the embeddings to not have gender correlation in them instead of modifying them afterwards. And there's been some follow-up work with other things, other approaches towards doing retraining. These are expensive to actually retrain, and you'd want to retrain. If you're going to do retraining, you'd want to do it on the biggest data set possible. Glove does not performs better when trained on Common Crawl, which is basically the entire internet, than just Wikipedia on various tasks. And these contextual ones, which are even harder to train, perform better. The Roberta, which has more data and other things, performs better than Elmo. And these can be very expensive to train. There might be some kind of some reasons you should be concerned about training these big models over and over again. Whereas the techniques we showed today, they can be done inside of this demo on basically inside your browser. So they're much more efficient to do, and they can be done on task. Okay, so there's a question in the chat. How do we know that quashing undesired correlation doesn't get rid of valid, so benign information at the same time? Yeah, so this is a great question. There are two types. I like to think of this in two ways of types of associations. There's the one where we think about this from this perspective, where we can actually measure this deficitly gendered information. You can kind of reverse the role in the wheat test. We called it wheat star at some point, and the kind of measures how much stereotypical information you might want to retain is still there. And you can also set up these natural language inference tasks to measure that, specifically with something like gender. But another context is just some more general downstream tasks, right? There are a bunch of benchmarks where these word vector embeddings are used in these benchmarks. I think, as we'll see a bit later, we'll see that I think one of my next slides, that we'll see that or if we didn't see it already, the dev and the test score on these sort of tasks are basically the same. For the general task, we haven't lost specific information, but on for something like this iterative null space approach, it will lose some specifically gendered information. Okay, so if you want to get rid of national origin versus good bad, do you also lose the correlations to religion and geography? Yeah, so this is an interesting question. So if you were, I suspect the answer, I'll speculate. I suspect the answer, if you use something like, you could do like linear projection with PCA, which you can only do once. I don't think you can do that repeatedly with INLP. But because that would require a binary notion, but you could do this linear projection with a PCA defined subspace with nationality. You might lose some correlation between religion and geography. But if you were to do something like this with Oscar, more of it might be retained. But it's a great question. I don't know the answer, and I encourage you to try and find out. Yeah, it's a great question. Yeah, and so as this is shown, this could be task specific. We might want to change which we're trying to remove based on what we need to retain, and that may not be expected ahead of time. So we'd rather be able to do this on the fly, and these lightweight mechanisms allow us to do that. Okay, are these results actually sensational? Yeah, so here's a table. This is a natural language inference task. You can see the dev and the test scores generally are, there's not too much loss. Hard to biasing manipulates subsets of points in a weird way. It lost a little bit more, but for instance, on Roberta, where we're only modifying the first layer, you're not seeing a lot of loss in performance. And with Oscar and linear projection, you're not seeing too much either. So on these general tasks, you're not losing too much. On these individual tasks, and we've shown this in a few contexts, but not in all of them. There's great stuff to look ahead in the next part of the discussion. Yeah, so let me kind of stop sharing my slides as I transition. So Vivek is going to give the last kind of wrap up discussion of the tutorial, and maybe I can try and answer some questions as he's getting ready. And some of these may be great questions that we had planned to pose, but the slides are going to be posted in if they aren't posted now, by the end of the day off of the website. Okay, so as Vivek is getting ready.
I'm about to share my screen.
Apart from natural language inference, what other tasks where we can see some improvements with device embeddings? We explored a little bit co-reference, sort of tasks, but those are noisy. It was harder to isolate the exact thing we were trying to measure. The general neutral embeddings had some work showing some progress on co-reference tasks. Do you have any other general ones in mind? We felt that was the most cleanest probe we could come up with. But how to show this conclusively in other downstream examples is a great question.
This is actually, it turns out, a harder question to answer because it requires us to train models, and standard test sets may not be suited for probing for bias. Sentiment analysis might be worth considering. It's another task that's worth considering because especially for things like nationality and race and religion.
There is a data set which does that.
Yeah, exactly. I think there is a data set which explores that question. Okay, we have maybe 5 to 10 minutes.
Slides. It just shows your.
I'm not sharing.
It just shows your home screen.
Oh, that's not good. Is this any better?
Yep, that's good.
Okay, cool. So we have about 10 minutes left, right? So I'm going to very quickly run through this thing. So we talked about bias all the time for the last 3 hours. When I would like to reintroduce the quotes around the word bias, because it can describe different kinds of behaviors, as Jeff mentioned at the beginning. And these can be, we looked at specifically stereotypical associations of different concepts, but they can be there might be other ways in which the word bias might be conceptualized. Another thing that's worth thinking about is the full context of the NLP application. And who is being harmed, why is it harmful, and why might debiasing actually help the person who is being harmed, rather in addition to just thinking of the representations themselves. This is the difference between representational and allocational harms that we saw earlier, and it's worth thinking about the full pipeline. Of course, it's important to have other groups of researchers, other communities involved in this discussion, and this is there are many other communities are rightfully involved outside of NLP, outside of machine learning, outside AI, outside computer science even. There was a question in the chat about multiple kinds of bias. This is the notion of intersectionality. How do we remove these different kinds of biases from the embeddings? And how can we probe for this? And we don't have answers to these questions. It's really a set of questions that I think may be open research questions to think about. If you want to remove multiple dimensions of bias, how do we do it? And how do we do it without destroying information? There's this contentious question of whether gender is binary at all. All the mechanisms that we saw treated gender as a binary construct. How do we extend this to non-binary notions of gender? It turns out that most of the data sets that we have treat gender in a binary fashion, and so the binary signal defined by, say, the direction between he and she is strong. The pronouns that are non-binary or neutral are either they are not used enough in the training data for the word embeddings, that like Latinx, that they don't have the what do you call it, the enough statistical support to get good embeddings, or they're generic like they and them. So there's various aspects like the plural neutral gender is confounded. This is extending the kinds of ideas that we saw to beyond the binary definition of gender is an open question. Another thing that's important to think about is, there is a world out there that doesn't necessarily use English, and in other languages. So the idea of gender is treated differently. So in German, nouns are associated with a gender, and depending on what the noun is, you use different pronouns, either der or die. Similarly in Spanish. How does bias play a role in this? In particular, for example, in applications involving translation, a worthy direction for exploration. And distributed vector embeddings are not just used for words, but also to encode other concepts, like, for example, images or merchants and knowledge graphs and regions and data sets or databases even. So do similar kinds of biases exist in these embeddings? Are there maybe linearly aligned concepts that we can identify and squash like we saw before? Again, worth exploring. There's a question, are the techniques transferable to other languages? The most of the work, unfortunately, I suspect is in the context of English, but I don't think, as Jeff says, it's been thoroughly explored. The final discussion point that I wanted to raise is that today's NLP is largely built on contextual embeddings. We saw some questions about some ideas for debiasing contextualized embeddings by essentially adjusting the first layer. The first layer even with embeddings like Elmo and Bert and Roberta are essentially not contextual. So there we can plug in the debiasing mechanisms that we saw, but how do we extend the approach of debiasing to contextualized embeddings. There is some early directions of work in the space, but again, it's worth exploring. What we did see in this tutorial, so there's a question, why did we only try the first layer? What was the rationale behind it? The answer is that the first layer is not contextual. So we can actually apply this approach at the first layer and make it work. If you essentially move the points the way we described beyond the first layer, what happens is the notion of bias might be reintroduced through other mechanisms. The context might introduce bias. So there's an issue there. And the things we found out that the directions that define various protected groups, for example, are more diffuse. So the same approaches that work for the non-contextualized embeddings don't directly work well enough if we debias the entire BERT stack, for example, or only apply it to the last layer. What we did see in this tutorial is an overview of how word embeddings might carry stereotypical associations. We saw a collection of methods for debiasing word embeddings that were specifically post-processing methods, rather that were essentially fast enough to and computationally efficient enough that you can actually run it inside your browser. And that idea gives us this new interactive tool that allows us to explore stereotypical associations in embeddings. You can try out your own word embeddings, for example, with this tool, or you can also see how debiasing methods operate on those associations. So as I say, as I think we've mentioned multiple times, we invite you to play with this tool, and hopefully it will allow you to kind of invent new ideas and explore new things. Thank you so much for your time. We would really appreciate it if you give us some feedback on our tutorial. We'll post a link to the feedback form in the chat. So please do take a few minutes to answer this short survey, and we'll be around if there are any questions or comments or discussions. We'll also monitor the Rocket chat forum. And if there's nothing else, I'm going to stop sharing my screen and open it up for questions.
Yeah, so thanks everyone for being here and asking all these great questions along the way.
And I think the slides have been posted on the website, and you can. There's a link in the chat, and also there's a link to the survey in the chat. Yes. Are there any questions?
I would also suggest if we also stop recording, I think then people can also have more free form discussion as well.